Hello and welcome back. I'm so glad you're here tonight. If you're new to this channel, my name is the Sleepy Scientist, and what we do here is a little different. We're not trying to keep you awake with flashing graphics or dramatic music. Instead, we're going to learn together, really learn, while you gradually, peacefully drift towards sleep. There's no test at the end, no pressure to remember everything, just the quiet pleasure of discovery, the kind that settles into your mind like snow falling on a winter evening. Tonight we're traveling to Saturn, the ringed giant, the jewel of our solar system, a world so beautiful that even the most hardened scientist can't help but pause when they see it through a telescope for the first time. Saturn is a planet that rewards patience. It moves slowly through our sky, taking nearly 30 Earth years to complete a single orbit around the Sun. And tonight, we'll move slowly, too, taking our time with each discovery, letting the wonder accumulate gradually, the way Saturn's rings themselves might have formed, particle by particle, moment by moment. Before we begin, I'd love to hear from you. How was your day? Was it the kind of day that flew by or one that lingered? Drop a comment below and let me know. And if you haven't already, consider subscribing to the channel. It helps more people find these quiet corners of the internet where learning doesn't have to be frantic or urgent. It can just be gentle. All right, get comfortable, adjust your pillow, let your breathing slow. The universe isn't going anywhere, and neither are we. Now let's begin. Let's start with something simple, something to anchor us. Saturn is the 6th planet from the Sun. If you were to line up all the planets in order, Mercury, Venus, Earth, Mars, Jupiter, and then Saturn, it would be sitting there patiently, about 1.4 billion kilometers away from the warmth of our star. That's nearly 10 times farther from the Sun than we are, and it's big, remarkably big. Only Jupiter, its neighboring giant, is larger. But here's where Saturn becomes truly strange, in the most delightful way. Despite being the second largest planet in our solar system, despite having a volume that could fit 764 Earths inside it, Saturn is so light, so remarkably lacking in density, that if you could find an ocean big enough to hold it, the planet would float. Actually float, like a beach ball bobbing on the surface of a cosmic sea. This isn't a metaphor or poetic exaggeration. Saturn's density is less than water. It's composed mostly of hydrogen and helium, the lightest elements in the universe, giving it a density of just 0.687 grams per cubic centimeter. Water, by comparison, is exactly 1.0. Of course, there's no ocean large enough. And even if there were, the gravitational forces involved would tear both Saturn and the ocean apart long before you could see whether it would sink or swim. But the fact remains, Saturn is a giant that somehow feels light, airy, as if the universe, in its infinite creativity, decided to build something enormous out of nearly nothing at all. And maybe that's a good place to start tonight, with the idea that size and mass don't always go hand in hand, that something can be vast and yet somehow gentle, taking up enormous space without weighing heavily on the cosmos around it. Time moves differently on Saturn. If you were somehow standing on a platform floating in Saturn's upper atmosphere, an impossible thought experiment, but bear with me, you would have to wait 29.5 Earth years to celebrate your first birthday. 29.5 years. Think about that for a moment. If you were born on Saturn at the same time you were born here on Earth, your Earth self would have graduated from high school, perhaps finished college, maybe started a career, fallen in love, experienced heartbreak, moved to different cities, lived nearly a third of a human lifetime. And your Saturn self, still waiting to blow out the candles on that first birthday cake. This slow, patient orbit is part of what makes Saturn feel so timeless when we observe it from Earth. Ancient humans, watching the night sky without telescopes, noticed that Saturn moved more slowly than the other visible planets. Mars could zip across the zodiac in a couple of years. Jupiter took 12, but Saturn took its time. Nearly 3 decades to complete its celestial journey. The Romans named it after Saturnus, their god of time and agriculture, the patient, measured passage of seasons, the slow accumulation of years. They couldn't have known how fitting that name would be. Perhaps there's something comforting in that slowness. In a world where everything seems to accelerate, where information moves at the speed of light and attention spans shrink by the year, Saturn is a reminder that some things can't be rushed. Some journeys take time, and that's not a flaw. It's just how it is. Saturn moves through space at its own pace, indifferent to our need for speed, content in its 29-year waltz around the sun. But while Saturn's year is achingly long, its day is startlingly short. A single rotation, one complete spin on its axis, takes only about 10 hours and 33 minutes. For a planet so enormous, this is almost absurdly fast. Imagine a ballet dancer spinning on one foot, but the dancer is nearly 10 times the width of Earth, and they're completing a full rotation in just over 10 hours. The forces involved are difficult to comprehend. This rapid rotation has consequences. Saturn spins so quickly that centrifugal force, the outward push created by its spinning motion, causes the planet to bulge noticeably at its equator. If you could somehow measure Saturn's diameter from pole to pole and compare it to its diameter across the equator, you'd find that the equatorial diameter is about 10% larger. Saturn isn't a perfect sphere. It's an oblate spheroid, flattened at the poles and swollen at the middle like a slightly squashed ball. In fact, Saturn is the flattest planet in our solar system, a distinction that comes directly from those brief, frenetic days. There's something almost contradictory about Saturn, this giant that moves so slowly through the solar system, but spins so rapidly on its own axis. Perhaps it's fitting. Perhaps Saturn is teaching us that time isn't uniform, that it stretches and compresses depending on where you are and what you're measuring. A year can be long, a day can be short. Both can be true at once. And maybe, as you lie there, feeling the weight of your own day beginning to lift, that's worth considering. That time is flexible, that there are pockets of the universe where it moves faster or slower, and that our perception of it is just one small slice of a much larger, stranger reality. In 1610, a man in Italy named Galileo Galilei pointed a homemade telescope at Saturn and saw something that confused him deeply. Through his primitive lens, barely more powerful than a modern pair of binoculars, Saturn didn't look like a single sphere. It looked like it had ears, or perhaps handles, like an old-fashioned teacup. He wrote in his notes that Saturn appeared triple-bodied, as if the planet had 2 smaller companions attached to its sides. He had no explanation for this, no framework to understand what he was witnessing, And then in 1612, something even stranger happened. The ears disappeared. Galileo looked again, expecting to see that peculiar three-part shape, and instead found only a solitary sphere. Saturn had returned to being, as far as he could tell, perfectly ordinary. He was baffled, perhaps even a bit disturbed. What kind of celestial body changes its fundamental shape within 2 years? He never solved the mystery. He died in 1642, still uncertain about what he had seen that night in 1610. It wasn't until 1655, more than 4 decades after Galileo's initial observation, that a Dutch astronomer named Christian Huygens, using a more powerful telescope, finally understood. Saturn didn't have ears or companions. It had rings, a flat, thin disk of material encircling the planet. And the reason Galileo's ears had disappeared in 1612 was simple. Earth had crossed Saturn's ring plane, viewing the rings edge on. Since the rings are incredibly thin, in most places only about 10 meters thick, when viewed from the side, they became nearly invisible, even through a telescope. Imagine being Galileo. Imagine seeing something unprecedented, something that doesn't fit into any existing category, and then having it vanish without explanation. Perhaps he went to his grave thinking he had hallucinated those ears, or that his telescope had deceived him. But he hadn't. He had seen something real, something extraordinary. He just lacked the tools, both technological and conceptual, to understand it. And perhaps that's a gentle reminder, as we drift here together, that there are things we don't yet understand, patterns we can't quite see, mysteries that won't be solved in our lifetimes. And that's okay. The universe doesn't owe us immediate answers. Saturn glows with a soft golden yellow hue. When you see it through a telescope or in photographs sent back from spacecraft, it doesn't have the angry red storms of Jupiter or the bright blue clarity of Uranus. Instead, Saturn looks almost serene, like honey, or aged parchment, or the warm light of a candle seen through frosted glass. That color comes from ammonia, tiny crystals of frozen ammonia suspended in Saturn's upper atmosphere, scattering sunlight in just the right way to produce that characteristic golden glow. Beneath those clouds, beneath that calm, uniform surface, lies something far more turbulent. Saturn's atmosphere is a roiling mixture of hydrogen and helium, driven by powerful winds and enormous storms. But we don't see that chaos directly. What we see is the haze of ammonia crystals, softening everything, creating the illusion of tranquility. It's a bit like looking at the surface of a calm lake. The water might appear smooth and still, but beneath there could be currents and creatures and complex ecosystems moving in ways the surface doesn't reveal. Perhaps that's why Saturn feels so inviting, even though it's a hostile environment where the temperatures at the cloud tops hover around 178 degrees Celsius, 288 degrees. Perhaps that golden color, that gentle appearance, speaks to something in us, the same part of our minds that finds comfort in warm light, in the glow of sunset, in the soft illumination that makes a room feel safe. Saturn looks the way a distant, unreachable place should look, beautiful, mysterious, and just a little bit like home, even though it's nothing like home at all. Let's return to that strange fact we touched on earlier, because it really is worth lingering over. Saturn is 95 times more massive than Earth. If you could somehow scoop up all the matter in Saturn and all the matter in Earth and weigh them on a cosmic scale, Saturn would tip that scale dramatically. 95 Earths wouldn't be enough to balance it. And yet, And this is the part that feels almost impossible. Saturn's density is less than water. Density is just mass divided by volume. It tells you how much stuff is packed into a given amount of space. Earth has a high density because it's made mostly of rock and metal, heavy elements compressed under gravity. Saturn, on the other hand, is made mostly of hydrogen and helium, the two lightest elements in the universe. These elements take up enormous amounts of space while weighing very little. The result? A planet that's gigantic but somehow fluffy. Not fluffy in the sense of cotton candy, of course. Saturn's interior is a hellish landscape of crushing pressures and searing temperatures, but fluffy in the sense that there's a lot of empty space between the atoms, a lot of volume without much mass. This is why Saturn could, theoretically, float on water. Its density, 0.687 grams per cubic centimeter, is less than water's 1.0. Of course, this thought experiment falls apart immediately when you consider the practicalities. Where would you find that much water? How would you keep Saturn from simply sinking into the water and displacing it, or from the gravitational forces tearing everything apart? But still, the fact remains. Saturn, for all its size and grandeur, is lighter than the oceans of Earth. And maybe there's something beautiful in that impossibility. Something that reminds us that the universe doesn't always behave the way our intuition expects. Sometimes the largest things are the lightest. Sometimes what seems solid is mostly space. Sometimes the rules we think we understand bend in ways that make us reconsider everything. If you could somehow stand on Saturn, another impossible thought experiment, since Saturn has no solid surface, the cold would be unimaginable. The temperature at the cloud tops, where our spacecraft take their measurements, is around 178 degrees Celsius. That's 288 degrees. To put that in perspective, the coldest temperature ever recorded on Earth was 89.2 degrees, 28.6 degrees, at a Soviet research station in Antarctica. Saturn's atmosphere is nearly twice as cold as the coldest place on Earth. At those temperatures, almost everything we think of as a gas would freeze solid. Methane, ammonia, water vapor, they don't exist as vapors at 178 degrees Celsius. They crystallize, forming clouds and hazes and frost that drift through Saturn's skies. But here's where it gets strange. Deep below those frozen clouds at the core of Saturn, temperatures soar to around 11,700 degrees, 21,000 degrees. That's hotter than the surface of the Sun. The Sun's surface, its photosphere, clocks in at about 5,500 degrees Celsius, 932 degrees Celsius. So Saturn, this cold, distant world, has an interior that's more than twice as hot as the surface of our star. How is that possible? The answer lies in pressure and heat left over from Saturn's formation. When Saturn first coalesced from the solar nebula 4.5 billion years ago, gravitational energy was converted into heat. That primordial heat is still there, trapped deep within the planet, unable to escape quickly. Additionally, as we'll discuss later, helium rain falling through Saturn's interior releases even more heat through gravitational friction. So Saturn is, in a very real sense, still cooling down from its birth. It's still radiating the warmth of its creation, even as its outer layers freeze in the darkness of space. It's a planet of extremes, frozen on the outside, blazing on the inside, existing in a state of tension between the two. And maybe, as you lie there, feeling the warmth of your blankets against the cool air of your room, you can appreciate that balance. The way comfort comes from the interplay between warmth and cold. between holding on to heat and letting it go. Saturn glows. Not visibly, of course, not in the wavelengths of light our eyes can detect. But if you could see in infrared, if you could perceive heat the way a thermal camera does, Saturn would appear as a luminous sphere, radiating far more energy than it receives from the distant sun. In fact, Saturn emits about 2.5 times more energy than it absorbs from sunlight. This isn't a small discrepancy. This is a planet that's actively generating its own heat, pumping warmth into the void of space at a rate that shouldn't be possible if solar radiation were its only energy source. Where does that extra energy come from? The primary answer, scientists believe, is helium rain. Deep within Saturn, below the visible clouds, below the layers of gaseous hydrogen, the pressure becomes so intense that helium, normally lighter than hydrogen, begins to condense into droplets. These droplets, denser than the surrounding hydrogen, start to fall. They sink deeper into the planet, pulled by Saturn's gravity. And as they fall, they release energy. It's the same principle behind hydroelectric power on Earth. Falling water turns turbines and generates electricity. Falling helium, in Saturn's case, generates heat. This process has been ongoing for billions of years. Slowly, imperceptibly, helium is separating from hydrogen and settling toward Saturn's core, releasing gravitational energy as it descends. The result is a planet that still radiates the warmth of its formation, a world that hasn't yet reached thermal equilibrium with its environment. Saturn is, in a sense, still being born. It's still in the process of cooling and settling, even though it formed 4.5 billion years ago. And maybe there's something comforting in that. The idea that even ancient things can still be in transition, still changing, still radiating the energy of their beginnings. Nothing is ever truly finished. Everything is still becoming. Volume is difficult to visualize when the numbers get this large. Saying Saturn is big doesn't quite capture it. So let's try this. If Saturn were hollow, a vast, empty shell, you could fit approximately 764 Earths inside it. 764. Imagine all the continents, all the oceans, all the mountains and forests and cities of Earth. Now imagine 764 of them, packed together inside Saturn's boundaries. And there would still be room left over, because planets don't tessellate perfectly. There are gaps between them, wasted space where spheres don't quite touch. But Saturn isn't hollow. That enormous volume is filled with hydrogen and helium, swirling in complex patterns, compressed by gravity into densities that increase as you descend toward the core. Near the surface, Saturn's atmosphere is thin, almost wispy. Deeper down, the hydrogen becomes liquid. Deeper still, it transforms into metallic hydrogen, a strange state of matter that conducts electricity like a metal but flows like a liquid. And at the very center, if our models are correct, there might be a small rocky core, a remnant of the planet's original formation, crushed under pressures we can barely imagine. All of that, all those layers, all that complexity, exists within a volume large enough to hold 764 Earths. And yet, as we established earlier, Saturn's mass is only about 95 times Earth's mass, which means most of Saturn is space, empty space between atoms. Hydrogen and helium atoms spread out across vast distances, filling an enormous volume without contributing much weight. It's a planet made of almost nothing, and yet it's one of the most magnificent objects in our solar system. Maybe that's worth considering as you drift towards sleep, that sometimes the most beautiful things are made mostly of emptiness, that grandeur doesn't always require density or solidity, that something can be vast and light at the same time. Saturn doesn't require telescopes or spacecraft to be seen. It's been visible to human eyes for as long as humans have looked up at the night sky. Ancient civilizations, the Babylonians, the Greeks, the Romans, the Chinese, all tracked Saturn's movement across the sky, noting its slow, patient journey through the constellations. They couldn't see the rings, of course. They couldn't perceive the hexagonal storm at the North Pole or the geysers of Enceladus, but they could see the planet itself, a bright yellowish point of light that didn't twinkle the way stars do. Stars twinkle because they're so far away that their light is effectively coming from a single point, and Earth's turbulent atmosphere bends and distorts that point of light, making it flicker. Planets, being much closer, appear as tiny disks rather than points. Their light is more stable, less prone to atmospheric distortion. So even without understanding the physics, ancient observers noticed that Saturn behaved differently than the stars around it. It moved slowly against the fixed backdrop of constellations. It shone with a steadier light. It was, clearly, something different. The Romans named it Saturnus, after their god of time, agriculture, and wealth, a deity associated with the slow, cyclical nature of seasons and the passage of years. It was a fitting name for a planet that took nearly 3 decades to complete its orbit, moving through the sky at a pace that mirrored the long rhythms of human life. When you were a child, Saturn was in one part of the sky. By the time you reached adulthood, it had moved to another. By the time you reached old age, it had completed its journey and returned, closing the circle. Perhaps there's something profound in the fact that Saturn has been with us all along, long before we understood what planets were, long before we had the tools to explore space, long before we knew about rings or moons or helium rain. Saturn was there, patient and unchanging, moving through its slow orbit while civilizations rose and fell beneath it. And it will still be there long after we're gone, continuing its journey, indifferent to our fleeting presence, but somehow, in its persistence, offering a kind of comfort. Some things endure, some things remain. We touched on this naming briefly, but it's worth dwelling on the symbolism a bit longer. Saturnus wasn't just any Roman deity. He was the god of agriculture, of planting and harvest, of the patient work of tending crops through seasons. He represented the slow accumulation of wealth through careful cultivation, the understanding that some things cannot be rushed. You plant in spring, tend through summer, and harvest in fall. There are no shortcuts. Time must pass. But Saturnus was also associated with time itself, with the passage of years, the aging process, the inevitable march toward endings. The Romans celebrated Saturnalia, a festival in his honor, during the winter solstice, the darkest time of year, when the sun seemed to stand still before slowly returning. It was a time of reflection, of looking back at the year that had passed, of preparing for the cycle to begin again. When the Romans looked up and saw that slow-moving golden light in the sky, taking nearly 30 years to complete its celestial circuit, the name Saturnus must have felt inevitable. Here was a wandering star that embodied patience, that moved through the heavens at the pace of a human generation, that seemed to measure time itself. The planet's motion mirrored the slow turning of seasons, the gradual accumulation of years, the understanding that some journeys cannot be abbreviated. And perhaps that's why Saturn still feels timeless to us today. Even now, when we've sent spacecraft to photograph its rings and probe its moons, Saturn retains that quality of patience. It doesn't demand our attention the way Mars does with its reddish glow, or Jupiter with its dramatic storms. Saturn just exists calmly, quietly, moving through space at its own pace, indifferent to our need for speed or excitement. It's a planet that rewards those who wait, who take their time, who understand that some things are worth the slow approach. And maybe, as you settle deeper into your pillow, that's a philosophy worth adopting. Not just for understanding Saturn, but for understanding life itself. When we call Saturn a gas giant, we're using a convenient shorthand, but it's not entirely accurate. Saturn isn't just gas. If it were, it would simply dissipate into space, spreading out until there was nothing left. Instead, Saturn is held together by gravity, its own mass pulling inward, compressing the hydrogen and helium into layers of increasing density. Near the top, where spacecraft fly and where sunlight still penetrates, barely, the atmosphere is genuinely gaseous, but descend deeper and the pressure builds. The hydrogen transitions from gas to liquid. Deeper still, and it becomes something stranger, metallic hydrogen, a state of matter that doesn't exist naturally anywhere on Earth. And at the very center, we think there might be a core, a small, rocky seed, perhaps 10 to 20 times the mass of Earth, made of heavier elements like iron, nickel, and rock. This core would be what remains from Saturn's original formation, the solid material that first coalesced from the solar nebula and then attracted all that hydrogen and helium through its gravitational pull. But we're not certain. We can't see Saturn's core directly. We can only infer its existence from gravitational measurements taken by spacecraft, from models of planetary formation, from our understanding of how gas giants come into being. If the core exists, it's buried beneath thousands upon thousands of kilometers of material, layers of liquid metallic hydrogen, layers of liquid molecular hydrogen, layers of gaseous hydrogen and helium. It's inaccessible, not just with our current technology, but perhaps forever. There's no drilling to Saturn's center, no way to confirm directly what's down there. We have to trust the mathematics, the models, the indirect evidence. And maybe that's fitting for a planet like Saturn, a world that keeps its deepest secrets hidden, wrapped in layers we can observe but never fully penetrate. Some mysteries, it seems, prefer to remain mysteries. Saturn's atmosphere is constantly in motion. Jet streams circle the planet, bands of fast-moving air that flow in alternating directions, eastward at some latitudes, westward at others. Near the equator, these winds reach astonishing speeds, up to 1,800 kilometers per hour. That's about 118 miles per hour. To put that in perspective, the fastest winds ever recorded on Earth, inside tornadoes and hurricanes, barely exceed 400 kilometers per hour, 250 mph. Saturn's equatorial winds are more than 4 times faster, and yet despite these incredible speeds, Saturn's atmosphere maintains remarkably stable patterns. The jet streams don't wander or dissipate. They persist year after year, decade after decade, maintaining their structure with a consistency that seems almost impossible given the chaotic nature of fluid dynamics. Scientists still don't fully understand what drives these winds or why they remain so stable. On Earth, our weather is powered primarily by heat from the sun, which warms the equator more than the poles, creating temperature gradients that drive atmospheric circulation. But Saturn is so far from the sun, and its internal heat source is so significant that the balance between solar heating and internal heat becomes complex. Perhaps Saturn's winds are driven more by the planet's internal heat than by the sun. Perhaps the rapid rotation, those 10-hour days, plays a role, creating Coriolis forces that organize the atmosphere into stable bands. Or perhaps there's something about the depth of Saturn's atmosphere, the lack of a solid surface to create friction and slow things down, that allows these wind patterns to persist indefinitely once they're established. We don't know for certain, but there's something mesmerizing about the idea of winds that have been blowing for millions of years, moving at speeds that would tear apart any structure we could build, flowing in patterns that persist across centuries like rivers carved into the sky. Maybe as you lie there, you can imagine those winds, silent, invisible, impossibly fast, circling a world so far away that its light takes over an hour to reach us. Magnetic fields are, in a way, invisible architectures, scaffolding made of force rather than matter, shaping the space around a planet even though we can't see or touch them. Earth has a magnetic field, generated by the churning of molten iron in its core, and that field extends thousands of kilometers into space, deflecting solar wind and cosmic rays, protecting our atmosphere from being stripped away. Saturn has a magnetic field too, and it's enormous, about 578 times more powerful than Earth's. But here's what's strange. Saturn's magnetic field is almost perfectly aligned with its rotation axis. On Earth, the magnetic North Pole doesn't match the geographic North Pole. There's about an 11-degree offset. On Jupiter, the offset is about 10 degrees. On Uranus and Neptune, the offsets are even more dramatic, with magnetic fields tilted at wild angles to their rotation axes. But Saturn's magnetic field lines up almost exactly with its spin axis, with an offset of less than 1 degree. This is deeply puzzling. Most planetary magnetic fields are generated by dynamos, convective motion of electrically conductive fluids deep inside the planet. These dynamos are typically chaotic, asymmetric, and tilted relative to the planet's rotation. The fact that Saturn's field is so perfectly aligned suggests something unusual about the structure of its interior, something that forces the magnetic field into alignment. But what? We don't know. Some scientists have proposed that there's a thin layer of conducting material at a specific depth inside Saturn, aligned in such a way that it naturally produces a symmetric field. Others suggest that we're simply seeing a temporary state, and that given enough time, Saturn's magnetic field would eventually drift out of alignment like other planets. Or perhaps Saturn is just different. Perhaps there's something about its composition, its internal heat, its rotation rate, or its history that makes it unique in this way. The universe, after all, doesn't owe us consistency. Not every planet has to follow the same rules. And maybe, as you drift closer to sleep, you can find comfort in that. In the idea that even when we think we understand how something should work, nature can surprise us, can reveal patterns that don't fit our expectations, can remind us that there's always more to learn. Imagine standing on a hypothetical platform floating in Saturn's upper atmosphere, looking up at the sky. The sun would still be there, still the brightest object in the heavens, but it would look different, smaller, dimmer, about 100 times less intense than it appears from Earth. Not because the sun itself has changed, but because of distance. Saturn orbits at an average distance of about 1.4 billion kilometers from the sun, nearly 10 times farther than Earth. And light, like all forms of energy, weakens with distance according to an inverse square law. Double the distance, and the light becomes 1/4 as bright. 10 times the distance, and the light becomes 1/100th as bright. At that distance, the sun would appear as a brilliant point, too bright to look at directly, but small enough that you could cover it with the tip of your finger held at arm's length. The illumination it provides would be enough to see by. Saturn's clouds are still visible in photographs, still illuminated by that distant sunlight. But it would feel more like twilight than noon, a perpetual dusk perhaps, or the light you get on an overcast day on Earth. And yet that dim, distant sunlight is still enough to create the breathtaking beauty of Saturn's rings. When the geometry is right, when the sun, Saturn, and a spacecraft align in just the right way, the rings can be backlit, glowing like a luminous halo as sunlight filters through the ice particles. Those particles, each one following its own orbit, each one catching and scattering that faint light, create one of the most stunning sights in the solar system. A reminder that beauty doesn't always require intensity. Sometimes the most extraordinary things emerge from subtlety, from light that has traveled vast distances and arrived finally, gentle and soft, to illuminate something worth seeing. Let's turn our attention now to the rings themselves, the feature that makes Saturn unmistakable, the crown that sets it apart from every other world in our solar system. The rings are vast. From edge to edge, they span up to 282,000 kilometers, 175 in miles. To put that in perspective, the distance from Earth to the Moon is about 384,000 kilometers. Saturn's rings could nearly stretch across that entire distance. If you could somehow lay them flat and drive across them at highway speeds, it would take you years to reach the other side. And yet, despite this enormous width, the rings are astonishingly thin. In most places, they're only about 10 meters thick. 10 meters. That's about the height of a 3-story building. Some regions are even thinner, just a few meters. If you were to scale Saturn's rings down to the size of a piece of paper, that paper would be proportionally thousands of times thicker than the rings are relative to their diameter. They're not so much rings as they are impossibly flat sheets of ice and rock, spread across hundreds of thousands of kilometers of space. How does something so vast remain so thin? The answer is collisions. The ring particles are constantly bumping into each other, and when they do, any vertical motion, any movement up or down relative to the ring plane, gets damped out. It's a bit like a crowd of people in a room gradually settling into a single level as they jostle and adjust. Over time, the ring particles settle into a configuration where almost all of their motion is horizontal, orbiting Saturn in a flat disk. Gravity keeps them from flying away. Collisions keep them from spreading out vertically. The result is a structure so flat it almost defies imagination. A cosmic record, spinning in the void, visible across the solar system. If you could somehow scoop up a handful of material from Saturn's rings and examine it closely, you'd find that it's mostly ice, water ice to be specific, the same stuff that forms glaciers on Earth, that floats in your drinks, that you scrape off your windshield on cold mornings. About 99% of the ring material is frozen water, with just trace amounts of rock, dust, and organic compounds mixed in. This surprised scientists when they first realized it. Why would Saturn's rings be made of ice? Where did all that water come from? One possibility is that the rings formed from a moon, an icy moon, perhaps similar to Enceladus or Mimas, that wandered too close to Saturn and was torn apart by tidal forces. Another possibility is that the rings are primordial, leftover material from Saturn's formation that never coalesced into a moon. In either case, the dominance of water ice suggests that the rings formed in the outer solar system, where temperatures are cold enough for water to freeze and remain stable. But here's what's interesting. The ice isn't pure. Mixed in with it are small amounts of other materials, silicates, organic compounds, perhaps even iron. These contaminants are what give some parts of the rings a slightly reddish or darker tint, contrasting with the bright white of pure ice. And the proportions vary from place to place. Some regions of the rings are nearly pristine, reflecting almost all the light that hits them. Other regions are dirtier, more polluted, reflecting less light and appearing darker in images. Why the variation? Scientists aren't sure. Perhaps meteorites and comets have been bombarding the rings for millions of years, adding their own material to the mix. Perhaps particles from Saturn's moons, little moons embedded within the rings, sweeping up ice and leaving behind a trail of contaminants, are responsible. Or perhaps the rings are slowly eroding, and the darker material represents older ice that's been exposed to space radiation for longer periods. We don't know for certain, but there's something poetic about the idea that these rings, these vast, beautiful structures, are made of the most common substance we know, frozen and scattered across hundreds of thousands of kilometers, catching sunlight and turning it into one of nature's most spectacular displays. The rings are not uniform. They're not made of evenly distributed, identically sized particles. Instead, they're a chaotic mix, a spectrum of sizes ranging from microscopic dust grains, smaller than grains of sand, all the way up to chunks of ice and rock, the size of houses or small buildings. Some particles are so small they're influenced by Saturn's magnetic field and can levitate above the ring plane, suspended by electrical forces. Others are so massive they have their own gravitational pull, shepherding smaller particles and carving gaps in the rings. Each particle is essentially a tiny moon, following its own elliptical orbit around Saturn according to Kepler's laws. The smaller particles orbit slightly faster than the larger ones at the same distance, creating a differential velocity, a relative speed between particles that's constantly changing. When particles collide, which they do frequently, these collisions can be gentle or violent depending on the relative velocities involved. Gentle collisions might result in particles bouncing off each other, losing a bit of energy in the process. Violent collisions can shatter particles into smaller pieces, creating more dust and debris. Over time, this process grinds down the larger particles, breaking them into smaller and smaller fragments. It's a slow erosion, but it's constant. And it means that the rings are not static. They're dynamic, evolving systems where particles are constantly being broken apart, colliding, redistributing themselves according to the laws of orbital mechanics and collision dynamics. Imagine a vast, slow-motion demolition derby, stretching across hundreds of thousands of kilometers, where every impact sends ripples through the system, where nothing is permanent, where everything is in flux. That's Saturn's rings, a system in constant motion, constantly changing, even though to our eyes, watching from across the solar system, it appears frozen and eternal. When astronomers first started observing Saturn's rings in detail, they began naming the different sections they could distinguish. The brightest ring, visible even through modest telescopes, was called the A ring. A fainter ring inside it became the B ring. A gap between them, the Cassini division, was one of the first features identified. As telescopes improved, more rings were discovered, and each new discovery received the next letter in the alphabet: C, D, E, F, G. But here's the quirk. The letters were assigned in the order of discovery, not in the order of the ring's positions. So if you were to travel from Saturn's cloud tops outward through the ring system, you wouldn't encounter them in alphabetical order. Instead, you'd pass through the D ring first, the innermost, then C, then B, then the Cassini division, then A, then F, then G, and finally the enormous diffuse E ring, the outermost ring, extending farther from Saturn than any other. This naming convention is a historical artifact, a reminder that our understanding of Saturn has accumulated piece by piece, observation by observation, over centuries. Each letter represents a moment of discovery, someone peering through a telescope, noticing something new, adding another piece to the puzzle. And now we're left with a system that doesn't follow a logical order, but instead tells a story. The story of how knowledge is built gradually, sometimes haphazardly, always shaped by the limitations of the tools available and the curiosity of the people using them. Maybe there's something charming about that. Maybe the fact that Saturn's rings are labeled D, C, B, A, F, G, E, out of order, nonsensical at first glance, is a reminder that science isn't always tidy. It's a messy, human endeavor, full of quirks and accidents, and the accumulated decisions of countless people trying to make sense of the universe. If you were to point a small telescope at Saturn tonight, assuming the geometry is favorable and the rings are tilted toward Earth, the feature that would catch your eye immediately is the B ring. It's the brightest part of the ring system, the most opaque, the most densely packed with particles. In some photographs, it appears almost solid, like a continuous disk rather than a collection of individual pieces. And it's not just visually dominant, it's also the most massive ring, containing the bulk of the material in the entire ring system. Why is the B ring so much brighter and more massive than the others? Scientists aren't entirely sure. Part of the answer might be that the B ring has a higher density of particles, more material packed into the same amount of space, which means more surface area to reflect sunlight. Another part of the answer might be that the particles in the B ring are larger on average, or cleaner, less contaminated with dark material, making them more reflective. Or perhaps the B ring occupies a gravitational sweet spot where material naturally accumulates and remains stable over long periods. Whatever the reason, the B ring dominates the ring system, both visually and physically. When you look at Saturn, when you see that iconic silhouette with the rings stretching out on either side, most of what you're seeing is the B ring. It's the feature that makes Saturn recognizable at a glance, the element that transforms it from just another gas giant into something extraordinary. And maybe, as you close your eyes and imagine Saturn floating in the darkness, you can picture that bright band of ice particles, each one catching sunlight, each one contributing its tiny reflection to the collective glow that we see from 1 billion kilometers away. A glow bright enough to inspire wonder, bright enough to make us look up and ask questions, bright enough to remind us that beauty can emerge from simplicity, from countless small things working together to create something greater than themselves. The rings, despite their appearance of being continuous bands, are actually full of gaps, spaces where particles are sparse or absent entirely. Some of these gaps are narrow, just a few kilometers wide. Others, like the Cassini division, are vast, thousands of kilometers across. And the reason these gaps exist is gravity, specifically the gravitational influence of Saturn's many moons. Here's how it works. Imagine a small moon orbiting Saturn somewhere near or within the ring system. As it moves through its orbit, its gravity tugs on nearby ring particles, pulling them slightly toward the moon. For most particles, this tug is insignificant, just a tiny perturbation in their orbit that gets smoothed out over time. But for particles that happen to orbit at specific distances from Saturn, distances where their orbital period is a simple fraction of the moon's orbital period, something different happens. These particles encounter the moon's gravitational pull repeatedly, in the same place in their orbit, over and over again. Each encounter adds up, amplifying the effect until the particle's orbit is significantly altered. This is called an orbital resonance, and it's incredibly powerful. Particles caught in a resonance with the moon get nudged, gradually, until they're pushed out of that orbital region entirely. They either drift inward or outward, leaving behind a gap. The moon, in a sense, has swept its resonance zone clear of particles, carving a division in the rings. It's a bit like a parent pushing a child on a swing. If you push at random times, nothing much happens. But if you push at exactly the right moment, in sync with the swing's natural rhythm, each push builds on the last, and soon the child is soaring. The most famous example is the Cassini division, the large gap between the A and B rings. This gap is maintained primarily by Mimas, one of Saturn's inner moons. Particles orbiting in the Cassini division have orbital periods that are exactly half of Mimas's orbital period, a 1.2 resonance. Every 2 orbits they complete, Mimas completes 1, and the gravitational tug repeats. Over time, this clears out the region, creating the gap we see today. There are dozens of other resonances throughout the ring system, each one associated with a different moon, each one carving its own gap, or creating subtle waves and structures in the ring material. It's a delicate gravitational choreography, invisible to the eye but evident in the patterns it leaves behind. A reminder that even empty space can tell a story. Let's linger for a moment on the Cassini division, because it's worth appreciating just how vast it is. This gap between the A ring and the B ring spans about 4,800 kilometers, roughly 3,000 miles. To give you a sense of scale, the planet Mercury, the smallest planet in our solar system, has a diameter of about 4,880 kilometers, which means you could, theoretically, place Mercury inside the Cassini division, and it would fit with room to spare. But here's the interesting part. the Cassini division isn't actually empty. When early astronomers observed it through telescopes, it appeared dark compared to the bright rings on either side, and they assumed it was a true gap, a region devoid of material. But when spacecraft flew past Saturn and took close-up images, they revealed that the Cassini division contains fainter ringlets and scattered particles. It's not empty. It's just less dense than the regions around it. The particles that do exist there are spread out, reflecting less sunlight overall, which makes the division appear dark from a distance. So the Cassini division is more of a dimmer region than a true void. It's a place where resonances with Mimas and other moons have reduced the density of particles, but haven't eliminated them entirely. Some particles remain, perhaps because their orbits don't quite match the resonance conditions, or because they've been replenished by collisions that knock material into the region from neighboring rings. It's a dynamic equilibrium, particles being cleared out by gravitational resonances, while new particles slowly drift in to replace them. There's something almost poetic about that. A gap that isn't quite empty, a division that's more about relative brightness than absolute absence. It reminds us that in space, as in life, boundaries are often fuzzy, categories blur. What looks like emptiness from a distance can, upon closer inspection, reveal hidden complexity. And maybe as you lie there, drifting towards sleep, that's a comforting thought, that even the voids we perceive might contain something, some faint trace of presence, some reminder that nowhere in the universe is ever truly, completely empty. Here's something that might surprise you. Saturn's rings might not have been around for very long, at least not in cosmic terms. Saturn itself is 4.5 billion years old, formed at the same time as the rest of the solar system. But the rings? They might be only 100 million years old, maybe even younger. That means dinosaurs could have walked the Earth at a time when Saturn had no rings, or very different rings than the ones we see today. How do scientists know this? The evidence comes from several sources. First, the rings are very bright and relatively clean, mostly pure water ice with only trace amounts of contamination. If the rings had been around for billions of years, exposed to the constant bombardment of meteorites and cometary debris, they should be much dirtier. The ice should be mixed with more rock and organic material, darkened by impacts and cosmic radiation. But the rings are bright, which suggests they haven't been exposed to space for very long. Second, the rings are losing mass. They're constantly being eroded by processes like ring rain, tiny particles charged by ultraviolet light from the sun, pulled along Saturn's magnetic field lines, and eventually falling into the planet's atmosphere. Scientists estimate that the rings are losing material at a rate that would cause them to disappear entirely in about 100 million years. If you run the clock backward, if you assume the rings have been losing mass at this rate since they formed, you arrive at an age of roughly 100 million years, maybe a bit more. Of course, this is all still uncertain. It's possible the rings are older and have been replenished somehow, perhaps by periodic disruptions of moons that add fresh material. Or perhaps the erosion rate has varied over time, making our backward extrapolation unreliable. But the idea that Saturn's rings are temporary, that they're a fleeting phenomenon in the planet's long history, is both humbling and strangely beautiful. It means we're living at a special time, a time when Saturn happens to have rings. In another 100 million years, they might be gone. And if that's true, then every photograph of Saturn, every glimpse through a telescope, every moment we spend contemplating those rings is a kind of privilege. We're witnessing something that won't last forever, something rare, something precious simply because it exists now, but might not exist later. One of the leading theories for how Saturn's rings formed involves a moon, a small, icy moon, perhaps similar in composition to Enceladus or Mimas, that made a fatal mistake. It wandered too close to Saturn, and when it did, tidal forces tore it apart. Tidal forces are a consequence of gravity's weakening with distance. If you're orbiting close to a massive object like Saturn, the side of your body facing Saturn experiences slightly stronger gravity than the side facing away. For small objects, this difference is negligible, but for larger objects, especially objects that are loosely held together, this difference can be significant. The near side gets pulled harder than the far side, and if the object gets close enough, that differential pull becomes stronger than the object's own gravity holding it together. The object stretches, elongates, and eventually breaks apart. There's a specific distance called the Roche limit, inside which tidal forces will destroy any object held together only by its own gravity. For Saturn, that limit is about 2.5 times the planet's radius. Saturn's rings lie entirely within this limit, which means that if a moon ventured inside that boundary, perhaps nudged by a collision with another moon or perturbed by a gravitational interaction, it would have been torn apart, shredded by tidal forces into countless fragments. Those fragments would continue orbiting Saturn, colliding with each other, grinding themselves down over time, eventually spreading out into the flat, disc-like structure we see today. This is just a theory, of course. We can't rewind time and watch it happen, but it fits the evidence. It explains why the rings are made of ice, because icy moons are common in the outer solar system. It explains why the rings are so thin, because tidal forces would flatten the debris into a disk. And it explains why the rings might be young, because the event that destroyed the moon could have happened relatively recently. Perhaps billions of years from now, Saturn will capture another moon, or one of its existing moons will drift inward, and the process will repeat. Perhaps Saturn's rings are not a permanent feature, but a recurring one, a cycle of creation and destruction that plays out over hundreds of millions of years. And if that's true, then we're witnessing one chapter in a much longer story, a story that began long before us and will continue long after we're gone. Every moment, Saturn's rings are dying. Not dramatically, not suddenly, but quietly, steadily, inevitably. Tiny particles, ice grains charged by ultraviolet radiation from the sun, are being pulled along Saturn's magnetic field lines and falling into the planet's atmosphere. Scientists call this phenomenon ring rain, and it's happening constantly, all over the ring system. Here's how it works. Ultraviolet light from the sun hits the ice particles in the rings and knocks electrons off their surfaces, giving them an electric charge. These charged particles then interact with Saturn's magnetic field, which permeates the space around the planet. The magnetic field lines act like invisible pathways, and the charged particles spiral along them, slowly drifting inward towards Saturn's poles. Eventually, they enter the upper atmosphere, where they vaporize, adding water to Saturn's clouds. NASA's Cassini spacecraft, during its final orbits in 2017, measured the rate of this ring rain. The numbers are staggering. Saturn is losing ring material at a rate of roughly 10,000 kilograms per second. That's about 22,000 pounds every single second. Enough to fill an Olympic-sized swimming pool every half hour. At this rate, the rings will disappear entirely in about 100 million years. Maybe sooner, depending on other factors like meteorite bombardment and gravitational interactions with Saturn's moons. 100 million years sounds like a long time. And it is, by human standards. But in the lifespan of a planet, 4.5 billion years, and counting, it's barely a moment, a flash, a brief interlude. Saturn has existed for billions of years without rings, or with different rings, and it will exist for billions more after the current rings are gone. We just happen to be here, now, during this narrow window of time when Saturn has rings, when those rings catch sunlight and create beauty that inspires awe and wonder. It's a reminder, perhaps, that nothing lasts forever, not even the most magnificent structures in the universe. Everything is temporary, everything is fading, and maybe, in that impermanence, there's a certain kind of beauty, a beauty that comes from knowing that this moment, this configuration, this particular arrangement of ice and light and gravity will never exist again. Among all of Saturn's rings, the F ring is one of the strangest. It's narrow, just a few hundred kilometers wide, and it orbits beyond the main ring system, separated from the A ring by a gap. But what makes the F ring truly bizarre is its structure. It's not a smooth, uniform band like the other rings. Instead, it's braided, twisted, kinked, and clumped, with strands that weave in and out of each other like threads in a loosely woven rope. And the reason for this chaotic structure is two small moons, Prometheus and Pandora. These moons are called shepherd moons because they shepherd the ring material, keeping it confined through their gravitational influence. Prometheus orbits just inside the F ring, and Pandora orbits just outside it. As they move through their respective orbits, their gravity tugs on the ring particles, pulling them in different directions. Prometheus, the inner moon, orbits slightly faster than the ring particles, and as it passes by, it pulls particles outward, away from Saturn. Pandora, the outer moon, orbits slightly slower and pulls particles inward. The result is a constant gravitational tug-of-war that keeps the F ring confined to a narrow region. But the story doesn't end there. Prometheus and Pandora don't orbit in perfect circles. Their orbits are slightly elliptical, which means their distance from the F ring changes over time. When they're close, their gravitational influence is strong, creating dramatic kinks and clumps in the ring. When they're far, the influence weakens and the ring relaxes. The result is a constantly changing structure, braids that form and unravel, clumps that appear and dissipate, strands that twist and straighten. The F ring is dynamic in a way that no other ring is, changing on timescales of weeks or months rather than millions of years. There's something almost alive about the F ring. It writhes and shifts, responding to the gravitational nudges of its shepherds, never settling into a stable configuration. It's a reminder that even in the cold, sterile environment of space, even in systems governed entirely by physics and mathematics, there can be complexity and unpredictability. There can be patterns that emerge, dissolve, and re-emerge in slightly different forms. There can be beauty in chaos, structure in disorder, and change that never stops. Maybe as you drift towards sleep, you can imagine the F ring, those twisted strands of ice orbiting in the darkness, braiding and unbraiding themselves in response to forces too subtle to see but too powerful to ignore. If you thought the F ring was strange, wait until you hear about the E ring. It's Saturn's outermost ring, and it's absolutely enormous. The E ring extends from the orbit of Mimas, one of Saturn's inner moons, all the way out past the orbit of Titan, Saturn's largest moon. That's a span of more than 300,000 kilometers, 186,000 miles. It dwarfs all the other rings, encompassing a region of space so vast that it's difficult to comprehend. But here's the catch. The E ring is incredibly diffuse. The particles that make it up are spread so thinly that if you were floating in the middle of the E ring, you probably wouldn't even realize it. You might see a faint haze, a slight brightening in the direction of Saturn, but it would be subtle. The E ring isn't like the bright, dense rings closer to Saturn. It's more like a ghostly halo, a vast cloud of microscopic ice. Particles, each one smaller than a speck of dust, scattered across hundreds of thousands of kilometers. And where do these particles come from? The answer is Enceladus, this small moon orbiting right in the heart of the E ring, is constantly shooting plumes of water vapor and ice particles from its south polar region. These geysers, powered by tidal heating from Saturn's gravity, eject material into space at high velocity. Some of that material falls back onto Enceladus's surface, but much of it escapes into orbit around Saturn, forming the E ring. In a very real sense, Enceladus is painting the E ring with its own internal ocean, spewing water into space and creating this vast, tenuous structure that encircles Saturn. The E ring is constantly being replenished by Enceladus, but it's also constantly being lost. The particles don't stay in orbit forever. Some fall back onto Enceladus or other nearby moons. Others spiral inward toward Saturn or outward into space. The E ring exists in a dynamic equilibrium, material being added and removed at roughly equal rates, maintaining a structure that's temporary but persistent. And maybe there's a lesson in that. Maybe the E ring is a reminder that some things endure not because they're permanent, but because they're constantly renewed. Because even as parts of them fade or fall away, new material arrives to take their place. It's not immortality exactly, but it's a kind of continuity, a persistence through change, through constant creation and destruction, through the endless cycle of loss and renewal. One of the most beautiful sights in images of Saturn is the shadow the rings cast on the planet's clouds. Depending on the angle of the Sun and Saturn's position in its orbit, the rings can block sunlight from reaching certain latitudes on the planet, creating dark bands that stretch across Saturn's northern or southern hemisphere. These shadows are sharp and well-defined near the rings, but soften as they project down onto the planet's curved surface. The shadows shift with Saturn's seasons. Saturn's rotation axis is tilted about 26.7 degrees relative to its orbital plane, just like Earth's 23.5-degree tilt. This means Saturn experiences seasons, periods when the northern hemisphere is tilted toward the Sun, and periods when the southern hemisphere is tilted toward the Sun. But because Saturn's year is so long, 29.5 Earth years, each season lasts about 7 Earth years. During Saturn's northern summer, the Sun shines down on the northern hemisphere, and the rings cast shadows on the southern hemisphere. During northern winter, the opposite happens. the sun illuminates the southern hemisphere, and the rings cast shadows on the north. And twice during Saturn's orbit at the equinoxes, the sun aligns with Saturn's ring plane, and the shadows disappear entirely. For a brief period, the rings cast no shadows at all. They're edge-on to the sun, too thin to block light in any significant way. These shadow patterns create a kind of visual calendar, a way to mark the passage of time on Saturn. If you were to watch Saturn continuously over the course of its 29-year orbit, you'd see the shadows grow, shrink, shift from one hemisphere to the other, and briefly vanish before reappearing. It's a slow dance, a gradual change that unfolds over years and decades, but it's mesmerizing in its own way. And maybe, as you close your eyes, you can imagine those shadows, dark bands stretching across a golden planet, markers of time passing, silent witnesses to seasons that last longer than most human lives. Every 15 years or so, something remarkable happens. Saturn's rings seem to vanish. Not actually, of course. The rings are still there, still orbiting Saturn, still composed of billions of ice particles. But from Earth's perspective, they become so thin that they're nearly impossible to see, even through powerful telescopes. This happens when Earth crosses Saturn's ring plane, the flat disk in which the rings orbit. Remember, Saturn's rings are incredibly thin relative to their width. In most places, they're only about 10 meters thick, but they span hundreds of thousands of kilometers. If you were to view them edge-on, they'd appear as a razor-thin line, perhaps not visible at all, depending on the lighting and your viewing angle. And that's exactly what happens during ring plane crossings. Earth, Saturn, and the Sun align in such a way that we're looking at the rings edge-on. The vast, glorious ring system, the feature that makes Saturn one of the most beautiful objects in the solar system, reduces to a faint line or disappears entirely. This is what confused Galileo in 1612. He had seen Saturn's ears in 1610, but 2 years later, when Earth crossed the ring plane, they vanished. He didn't understand what he was seeing. He couldn't have known that the ears were actually rings, viewed at an angle, and that a shift in perspective could make them seemingly disappear. It must have been deeply unsettling, watching something inexplicable appear, then vanish, with no clear explanation. But now we understand. And there's something humbling about the fact that even the most magnificent structures can become invisible depending on your point of view. Saturn's rings haven't changed. They're still there, still vast, still beautiful. But from certain angles, they disappear. Perspective matters. How you look at something determines what you see. And maybe, as you drift towards sleep, that's worth remembering. That sometimes things we take for granted can vanish, not because they've ceased to exist, but because we've shifted our point of view. And sometimes, if we wait patiently, if we give time for perspectives to shift again, those things come back into view, as glorious and astonishing as they ever were. In 1980, when Voyager 1 flew past Saturn and sent back detailed images of the rings, scientists noticed something they hadn't expected: spokes. Dark, radial features stretching across the B-ring like spokes on a wheel. These weren't permanent structures. Time-lapse images showed them appearing, persisting for a few hours, and then fading away. New spokes would form in different locations, only to disappear as well. It was as if the rings were breathing, inhaling and exhaling these ghostly patterns at irregular intervals. What are the spokes? Even now, decades after their discovery, scientists aren't entirely certain. The leading theory is that they're caused by electrically charged dust particles, tiny grains of ice that have been charged by cosmic rays or ultraviolet light. These charged particles interact with Saturn's magnetic field, which rotates with the planet. The magnetic field sweeps through the rings like a rotating broom, and as it does, it lifts the charged particles slightly above the ring plane. These levitating particles form clouds, spokes, that hover above the ring surface, scattering light differently than the ring particles around them. But why do the spokes appear dark in some images and bright in others? It depends on the viewing angle and the way light scatters off the tiny particles. When viewed from certain angles, the spokes scatter light forward, making them appear bright against the darker ring. From other angles, they scatter light away from the observer, making them appear dark against the brighter ring. It's a trick of optics, a reminder that what we see depends not just on what's there, but on where we're standing and how the light happens to fall. The spokes are most visible around Saturn's equinoxes, the times when the sun aligns with the ring plane. During these periods, sunlight illuminates the ring's edge on, casting long shadows and highlighting vertical structures that would otherwise be invisible. It's as if the equinoxes open a window into a hidden dimension of the rings, revealing processes that are usually too subtle to detect. And then, as the angle changes, as Saturn continues its orbit and the sun shifts position, the spokes fade back into invisibility. They're still there, still forming and dissipating, but they become too faint to see, hidden once again, waiting for the next equinox to reveal themselves once more. As spacecraft cameras improved and scientists examined Saturn's rings in ever greater detail, they began noticing something peculiar: tiny gaps in the rings shaped like propellers. These weren't ordinary gaps. They had a distinctive double-lobed structure, like the blades of an airplane propeller, with a central bright spot where the two lobes met. And they were everywhere, scattered throughout the A-ring by the thousands. But here's the mystery. Scientists couldn't see what was creating these propellers. The central bright spot suggested something was there, some object embedded in the rings, but it was too small to be resolved directly, even by Cassini's high-resolution cameras. The objects creating these propellers, scientists eventually realized, are moonlets, tiny moons, perhaps only 100 meters across, roughly the length of a football field, orbiting within the rings themselves. These moonlets are too small to have much gravitational influence, but it's enough. As a moonlet orbits, its gravity pushes ring particles away on either side, creating two empty lobes, the propeller blades. The moonlet itself sits at the center, reflecting sunlight and appearing as a bright spot. It's like footprints in snow. You can't see the person who made them, but you can see the marks they left behind. And from those marks, you can infer their presence, their size, their direction of travel. The propellers revealed something profound. Saturn's rings aren't just passive collections of ice particles. They're active, dynamic systems populated by countless objects we can't see directly. Each propeller is evidence of a moonlet we didn't know existed, a tiny world carving its own path through the ice, leaving a signature that's visible only because of the way it disturbs the material around it. And if there are thousands of propellers, there must be thousands of moonlets, perhaps tens of thousands, perhaps more, each one orbiting silently, each one too small to detect except through its effects. It's a humbling thought. How much of the universe is like this? How many things exist that we can only perceive indirectly through the disturbances they create, the patterns they leave behind? How many invisible actors are shaping the systems we observe, too small or too faint or too distant to see, but present nonetheless, making their quiet contributions to the grand architecture of space? Maybe as you lie there, you can think of the propellers, those ghostly shapes in the rings, those signatures of presence without direct visibility, and wonder what else is out there, unseen but real, leaving traces we haven't yet learned to recognize. There's a small moon named Daphnis, only about 8 kilometers, 5 miles across, that orbits within a narrow gap in Saturn's A-ring called the Keeler Gap. Daphnis is so small that if you were standing on one end of it, you could probably see the opposite horizon without much difficulty. It's barely larger than a city, but despite its tiny size, Daphnis has a dramatic effect on the material around it. As Daphnis orbits through the Keeler Gap, its gravity tugs on the ring particles at the gap's edges. Because Daphnis's orbit isn't perfectly circular, it's slightly inclined relative to the ring plane. The moon moves up and down as well as side to side relative to the surrounding ring material. And as it does, it pulls ring particles vertically, creating waves. These aren't waves in the usual sense, not water lapping against a shore, but ripples in the ring material, vertical undulations that travel along the gap's edge, like ripples spreading across a pond. Images from Cassini show these waves clearly. They look like scalloped edges, a series of peaks and troughs that follow Daphnis as it orbits. The amplitude of the waves, their height, can be over 1 kilometer, towering above the otherwise flat ring plane. And as Daphnis continues its orbit, the waves propagate outward, spreading the disturbance across the ring. Eventually, collisions between ring particles damp the waves out, flattening them back into the ring plane. But by then, Daphnis has moved on and is creating new waves somewhere else in its orbit. It's a beautiful example of gravitational influence, a tiny moon, barely visible, creating patterns that are evident across thousands of kilometers. Daphnis doesn't need to be large to make an impact. Its gravity is weak, but it's consistent, persistent, applied over and over as the moon completes its orbit. And that persistence creates structure, creates order, creates waves that wouldn't exist without the moon's presence. Perhaps there's a metaphor there about how even small influences, applied consistently over time, can create visible effects, can shape the world around them, can leave marks that persist long after the moment of interaction has passed. Saturn's rings are bright, remarkably bright. They have an albedo, a measure of reflectivity, of about 0.6 to 0.8, depending on which part of the ring system you're looking at. That means they reflect between 60% and 80% of the sunlight that hits them. For comparison, fresh snow on Earth has an albedo of about 0.8 to 0.9. It's one of the most reflective natural surfaces we have. Saturn's rings are nearly as reflective as snow. This high reflectivity tells us something important. The ice particles in the rings are relatively pure and clean. If they were heavily contaminated with rock or organic material, if they were coated in dust or darkened by billions of years of cosmic radiation, they'd absorb more light and appear dimmer. But they don't. They shine brightly, catching sunlight and scattering it in all directions, creating the luminous appearance that makes Saturn so photogenic. But why are the rings so clean? That's still a bit of a mystery. One possibility is that the rings are young, only 100 million years old or so, and haven't had time to accumulate much contamination. Another possibility is that there's some process continually refreshing the ring particles, grinding away the outer layers, and exposing fresh ice underneath. Collisions between particles might do this, or perhaps micrometeorite impacts chip away at the surface, revealing pristine ice from within. Or perhaps the rings are cleaned by electrostatic processes, charged particles interacting with Saturn's magnetic field, carrying away dust and contaminants. We don't know for sure, but the result is undeniable. The rings are bright, reflective, beautiful. They catch light and throw it back into space, creating one of the most visually striking features in the solar system. And maybe, as you imagine those rings, those countless ice particles, each one gleaming, each one reflecting the distant sun, you can appreciate the way light transforms matter into something more than itself. Ice alone is just frozen water, but ice arranged in rings, reflecting sunlight across 1 billion kilometers of space, becomes art, becomes wonder, becomes something worth staying awake to contemplate, even as sleep begins to pull you gently downward. There's a hidden music in Saturn's rings. Not sound, of course. Space is a vacuum, and sound can't travel there. But a kind of mathematical harmony, a set of relationships between the orbits of ring particles and the orbits of Saturn's moons. These relationships, called orbital resonances, create the structure we see in the rings, the gaps, the divisions, the sharp edges that separate one ring from another. Here's how it works. Imagine a ring particle orbiting Saturn at a specific distance. Its orbital period, the time it takes to complete one orbit, depends on that distance. Now imagine a moon orbiting farther out. If the particle's orbital period happens to be a simple fraction of the moon's orbital period, say exactly half or exactly 1/3, then the particle and the moon will encounter each other at the same point in their respective orbits, over and over again. Each encounter adds up, amplifying the gravitational perturbation until the particle's orbit is significantly altered. This is the resonance effect we mentioned earlier. It's the reason the Cassini division exists. Particles orbiting in that region are in a 1.2 resonance with Mimas, encountering the moon's gravity repeatedly in the same location, which eventually nudges them out of the region. Other gaps and divisions are created by resonances with other moons: Janus, Prometheus, Pandora, Enceladus. Each moon contributes its own set of resonances, each one carving structure into the rings. But resonances don't just create gaps. They also create density waves, spiral patterns of higher and lower density that propagate through the ring material like ripples in a pond. These waves are subtle, not visible to the naked eye, but detectable in high-resolution images and in the way ring particles reflect light. They're evidence of the gravitational dialogue between the rings and the moons, a constant conversation conducted through the language of orbital mechanics, where simple ratios and repeating patterns create order from chaos. Perhaps you can think of it as a kind of cosmic music, a symphony where each moon is an instrument, each resonance a note, and the rings themselves are the score on which this music is written. It's a slow symphony playing out over years and centuries, inaudible but visible, silent but structured. And we, looking at Saturn from across the solar system, are the audience, witnessing a performance that's been ongoing for millions of years, that will continue long after we're gone, sustained by nothing more than gravity and geometry and the elegant mathematics that govern the motion of worlds. Saturn's rings are not static. They're not frozen in place, preserved forever in their current configuration. They're dynamic, constantly evolving, constantly changing in response to countless collisions between particles. Every second, trillions upon trillions of collisions occur throughout the ring system. Ice particles bumping into each other, bouncing off, transferring momentum and energy in ways that are individually insignificant but collectively profound. Each collision, no matter how gentle, results in a loss of energy. Energy is converted into heat, or into deforming the particles, or into breaking them into smaller fragments. And when energy is lost, orbits change. Particles that lose energy gradually spiral inward toward Saturn. Particles that gain energy spiral outward. The result is a slow redistribution of material, a gradual evolution of the ring system's structure. This process should, over time, cause the rings to collapse. If particles are constantly losing energy through collisions, they should gradually fall inward, raining down onto Saturn until nothing is left. And indeed, this is happening. It's the ring rain we discussed earlier. But the time scale is long. The rings won't disappear overnight, or even in 1,000,000 years. Current estimates suggest they have roughly 100 million years left before they're gone entirely. But here's the puzzle. If collisions cause the rings to decay, why are they still here? Saturn is 4.5 billion years old. If the rings have been colliding and decaying for all that time, they should have vanished long ago. The fact that they're still here, still bright and beautiful, suggests either that they're much younger than the planet itself, only 100 million years old or so, or that there's some process replenishing them, adding new material to replace what's lost. We don't know which explanation is correct. Perhaps both are true to some extent. Perhaps the rings are young, formed from a destroyed moon in Saturn's relatively recent past. Perhaps they're also being replenished, slowly, by material from Enceladus or other sources. Either way, the rings exist in a state of tension between the forces that create them and the forces that destroy them, between stability and decay, between permanence and impermanence. And maybe as you drift towards sleep, that tension feels familiar. We all exist in similar states, between growth and decline, between building and breaking down, between holding on and letting go. The rings are just doing what everything does, on scales both vast and small, persisting for a while, shining brightly, and then eventually fading away. Twice every 29.5 years, something extraordinary happens. Saturn reaches its equinox. The planet's tilt, which causes its seasons, brings the Sun directly in line with Saturn's equatorial plane, the same plane in which the rings orbit. For a brief period, sunlight illuminates the rings edge-on, shining horizontally across their surface rather than down from above or below. This unusual lighting creates dramatic effects. Normally, we see the rings from an angle. The sun illuminates them from one side, and we view them from another perspective. But during an equinox, The lighting geometry is perfect for revealing structures that are otherwise invisible, specifically vertical structures, particles or clumps that stick up above or below the otherwise flat ring plane, cast long shadows that stretch across the ring surface. Cassini was in orbit during Saturn's 2009 equinox, and the images it captured were stunning. Scientists saw shadows cast by the tiny moon Daphnis, revealing just how much the moon's gravity pulls ring particles vertically. They saw shadows from clumps and waves in the F ring, some of which towered more than 2 kilometers, 1.2 miles, above the ring plane. They saw features they'd never noticed before, subtle structures that only became visible when the lighting was just right. It was like shining a flashlight across a textured surface. Normally, if you look at a surface from directly above while lighting it from the same angle, it appears smooth. Shadows are minimized, and small irregularities disappear. But if you shine the light at a grazing angle, every tiny bump and dip casts a shadow, and the texture becomes obvious. Saturn's equinoxes do the same thing for the rings, revealing a hidden topography that exists in 3 dimensions, even though the rings appear 2-dimensional from most angles. These equinox observations reminded scientists that Saturn's rings aren't infinitely flat. They have thickness, structure, complexity in the vertical dimension, and they reminded us that sometimes, to see something clearly, you need the right perspective, the right angle, the right lighting, the right moment. Truth, it seems, depends on context. What's invisible from one angle becomes obvious from another. And maybe as you lie there in the darkness, you can think about what perspectives you might be missing, what truths might be hiding in plain sight, waiting for the right light to reveal them. If you zoom in on certain sections of Saturn's rings, particularly the A and B rings, you'll notice something remarkable: spiral patterns. Not quite like the spirals of a galaxy, but similar in principle. These are called spiral density waves, and they're created by gravitational resonances between ring particles and Saturn's moons. Here's how they form. Imagine a moon orbiting outside the rings, creating a resonance with particles at a specific distance. Every time the moon completes an orbit, it tugs on particles in the resonance zone, pulling them slightly outward. But ring particles near the resonance zone don't all respond in exactly the same way. Some are pulled more than others, depending on their exact distance from Saturn and their position in their orbit. The result is that particles bunch up in some regions and spread out in others, creating alternating bands of higher and lower density. Because Saturn rotates, and because the ring particles orbit at different speeds depending on their distance from the planet, these density variations don't stay in place. Instead, they spiral outward from the resonance location, creating a pattern that looks like the grooves on a vinyl record, or the arms of a spiral galaxy. The waves are tightly wound near the resonance and gradually open up as they propagate outward. These spiral density waves are fascinating because they're one of the few places in the solar system where we can observe wave mechanics on a grand scale. The same mathematics that describes sound waves propagating through air or water waves spreading across a pond also describes these density waves propagating through Saturn's rings. And interestingly, the same physics applies to spiral galaxies. The beautiful spiral arms we see in galaxies like the Milky Way are also density waves, places where stars and gas bunch up as they orbit the galactic center. So, in a sense, Saturn's rings are a laboratory for understanding galaxy formation. They're a place where gravitational physics plays out in ways we can observe directly, creating patterns that mirror structures billions of times larger and farther away. It's a reminder that the universe, for all its diversity, operates according to consistent principles, that the same laws that govern ice particles orbiting Saturn also govern stars orbiting galactic cores, that patterns repeat across scales, and that by studying the small, we can learn about the large. Almost all of Saturn's ring particles orbit in the same direction, counterclockwise as viewed from above Saturn's north pole. This is the natural consequence of how the rings formed. Whether they came from a destroyed moon or from leftover material from Saturn's formation, the initial angular momentum, the rotational motion, was in one direction, and that direction has been preserved over billions of years. But not every particle follows this rule. A small fraction of ring particles, perhaps 1 in a million or 1 in a billion, orbit in the opposite direction. They're retrograde particles, moving against the flow, like salmon swimming upstream. How did they get there? The answer is collisions. In the chaotic environment of the rings, where particles are constantly bumping into each other, occasionally a collision is violent enough to reverse a particle's direction entirely. Imagine 2 cars colliding head-on. Under the right circumstances, one car could be spun around and sent back the way it came. The same thing can happen with ring particles. A high-energy collision can flip a particle's orbit, sending it backward relative to the rest of the ring. These retrograde particles don't last long because they're moving in the opposite direction. Their relative velocity compared to other particles is much higher. When a prograde particle, moving with the flow, collides with a retrograde particle moving against it, the collision is much more violent than typical ring collisions. The particles might shatter, breaking into smaller fragments, or one might knock the other into a new orbit, perhaps flipping it back to prograde motion. Either way, retrograde particles are constantly being removed from the system, either destroyed or converted back to prograde orbits. But new retrograde particles are constantly being created through collisions, maintaining a small population that exists in a kind of dynamic equilibrium. It's a reminder that even in systems that appear ordered and stable, there are always outliers, particles that don't follow the rules, that move against the current, that exist in states that seem temporary or unstable, but persist nonetheless because they're constantly being recreated. And maybe there's something poetic in that, about how going against the flow is difficult, often short-lived, but always possible. About how even in the most structured systems, there's room for deviation, for particles or people who choose a different path, even if that path is harder, even if it doesn't last forever. The D ring is Saturn's innermost ring, and it's a strange place. Unlike the bright, well-defined rings farther out, the D ring is faint, diffuse, almost ghostly. It extends from the inner edge of the C ring down towards Saturn itself, reaching closer to the planet than any other ring material. And at its inner edge, something inevitable is happening. The particles are spiraling inward, falling towards Saturn, disappearing into the planet's atmosphere. This is the final stage of ring rain. Particles that have been charged by ultraviolet light, that have been nudged by magnetic fields, that have lost energy through collisions or other processes eventually find themselves in the D ring, on the last leg of their journey. Their orbits decay, bringing them closer and closer to Saturn with each pass, until finally they enter the atmosphere. There they vaporize, heated by friction with the tenuous gases at the top of Saturn's clouds, breaking apart and adding their water to the planet's chemistry. It's a one-way journey. Once a particle enters the D ring and begins spiraling inward, there's no escaping. Gravity wins. Saturn's enormous mass pulls the particle down, slowly but inexorably, until it's gone. And yet, the D ring persists. New particles arrive from the rings farther out, replenishing the material that's lost. The D ring exists in a state of constant flux, particles flowing in, particles flowing out. The structure maintained not by permanence, but by steady turnover. Perhaps it's fitting that the D ring is the last stop before oblivion. It's the place where ring particles end their existence, where they transition from being part of Saturn's magnificent ring system to being part of Saturn itself. And maybe there's something almost peaceful about that. After orbiting for millions of years, after countless collisions and interactions, after reflecting sunlight and contributing to the beauty of the rings, the particles finally come to rest. They fall into Saturn. They become part of the planet they've been orbiting all along, and in a sense, they return home. When we look at Saturn's rings today, we're seeing a snapshot, a single moment in a long, dynamic history. But the rings haven't always looked like this. They're evolving, changing, and if we could rewind time, we'd see them transform in ways that might be difficult to recognize. One intriguing possibility is that the rings were once much more massive. Perhaps they extended farther from Saturn, or were denser, containing many times more material than they do today. Over time, through processes like ring rain, meteorite bombardment, and gravitational interactions with moons, the rings have been eroded, losing mass and shrinking to their current size. If this is true, then what we see today is a remnant, a faded glory, still beautiful, but diminished from what once was. Another possibility is that the rings have cycled through multiple generations. Perhaps a moon was destroyed 100 million years ago, creating the rings we see today. But perhaps, billions of years before that, another moon was destroyed, creating a different ring system that eventually decayed and disappeared. And perhaps, in the future, another moon will be destroyed, or another source of material will create a new ring system, different from the current one. Saturn might be a planet that periodically wears rings, losing them and regaining them over geological timescales. We don't know for certain. We have only this one moment, this one configuration of rings to study. We can't observe Saturn's past directly, and we can't fast forward to see its future. All we can do is infer from the evidence available what might have been and what might be. And maybe that's a useful reminder about perspective and humility. We see the universe at one moment in time through one narrow window, and from that limited view, we try to understand the whole story. Sometimes we get it right, sometimes we're surprised, and always there's more to learn. When you look at detailed images of Saturn's rings, you might notice that they're not uniformly white. There are subtle color variations. Some regions appear brighter, almost bluish white, while others have a slight reddish or a tan tint. These color differences are faint, easy to miss if you're not looking carefully, but they're real, and they tell us something about the composition and structure of the ring material. The brightest, whitest regions are likely composed of the purest water ice, clean, relatively uncontaminated, reflecting light across all wavelengths equally. These are the regions that make Saturn's rings so dazzling, so photogenic. But the slightly reddish or darker regions suggest contamination. Perhaps there's a higher concentration of rocky material mixed in with the ice. Perhaps there are organic compounds, carbon-based molecules created when ultraviolet light breaks apart methane or other simple molecules. Or perhaps the particles in these regions are smaller, and smaller particles scatter light differently, creating a change in apparent color. Scientists have used spectroscopy, analyzing the wavelengths of light reflected by the rings, to investigate these color variations. They've found that the reddish tint often correlates with the presence of iron oxide or with organic tholins, complex molecules formed through radiation processing of simpler compounds. These materials are common in the outer solar system, found on many moons and asteroids, and their presence in the rings suggests that the ring material has been altered over time by exposure to sunlight, cosmic rays, and micrometeorite impacts. But the distribution of these contaminants isn't uniform. Some regions are cleaner than others. Some parts of the B ring are nearly pure ice, while parts of the C ring are noticeably darker. Why? Perhaps it has to do with the age of different ring regions. Older material has had more time to accumulate contaminants, or perhaps it's related to the source of the material, different moons or different events contributing material with different compositions. Or perhaps there are ongoing processes that clean some regions while leaving others dirty, creating the patchwork of colors we see today. Whatever the explanation, the color variations remind us that Saturn's rings are not monolithic. They're complex, heterogeneous, composed of countless individual particles, each with its own history, its own journey. And maybe there's beauty in that diversity, in the idea that even something as seemingly uniform as Saturn's rings contains multitudes, contains variations and differences that only become apparent when you look closely, when you take the time to notice the subtleties. You might imagine that Saturn's ring particles, being mostly ice, would stick together when they collide. After all, ice is somewhat sticky. Snowflakes cling to each other, forming snowballs and snowmen. But in Saturn's rings, the particles don't stick. They bounce off each other, maintaining their individual identities, remaining separate despite countless collisions. Why? The answer involves electrostatic forces. In the harsh environment of space, ring particles are constantly being bombarded by ultraviolet light from the sun and by charged particles from Saturn's magnetosphere. This bombardment knocks electrons off the surface of the ice particles, giving them an electric charge, and particles with the same charge repel each other. It's the same force that makes your hair stand up when you rub a balloon on it, or that makes clothes cling together when they come out of the dryer. This electrostatic repulsion prevents the particles from sticking together permanently. When two particles collide, the electrical repulsion pushes them apart before they can freeze or fuse into a single larger particle. It's a delicate balance, gravity and collisions trying to bring particles together, electrostatic forces keeping them apart. And the result is a ring system that remains granular, composed of countless individual particles rather than coalescing into a single solid disk. There's something almost miraculous about this. If the electrostatic forces were weaker, or if the particles weren't being charged by solar radiation, Saturn's rings might have collapsed long ago, clumping together into a few large moons or a solid ring. But instead, the rings persist in their current form, a vast, shimmering field of individual particles, each one maintaining its independence, each one contributing to the collective beauty without losing its identity. And maybe, as you drift towards sleep, you can think about that balance, about how systems are held together not just by forces that attract, but also by forces that repel, about how maintaining separation, maintaining individuality, can be just as important as coming together, about how the most beautiful structures sometimes emerge from a tension between opposing forces, from a dance between attraction and repulsion, connection and independence. Saturn's rings don't exist in perfect isolation. They interact with their environment, and one of the surprising discoveries from Cassini's mission is that the rings have their own atmosphere. It's incredibly thin, far less dense than Earth's atmosphere, or even than the thin atmospheres of Mars or Titan. But it's there, a haze of oxygen and water vapor extending above and below the ring plane, created by the rings themselves. How does this atmosphere form? The process begins with ultraviolet light from the sun. When UV photons strike water ice particles in the rings, they have enough energy to break apart the water molecules. H2O splits into hydrogen and oxygen. The hydrogen, being extremely light, escapes into space or is swept away by Saturn's magnetic field. But the oxygen remains, lingering near the rings, forming a tenuous cloud. Some of this oxygen combines with other atoms or molecules, forming compounds like O2, molecular oxygen, or OH, hydroxyl radicals. Some remains as individual oxygen atoms, drifting in the space above and below the rings. And occasionally, water molecules are ejected intact from the rings, knocked free by micrometeorite impacts or by the energy of collisions, adding to the atmosphere. This ring atmosphere is constantly being created and destroyed. UV light continuously breaks apart more water molecules, replenishing the oxygen. But the oxygen doesn't stay forever. Some falls back onto the rings, some is ionized and carried away by Saturn's magnetic field, some reacts with other materials. The result is a dynamic equilibrium, a thin veil of gas that surrounds the rings, invisible to the naked eye but detectable by sensitive instruments. Perhaps there's something poetic about the idea that the rings breathe, that they exhale oxygen and water vapor into space, creating an atmosphere from their own substance. It's a reminder that even in the vacuum of space, even in systems we think of as cold and inert, there's activity, there's chemistry, there's interaction between matter and energy, between light and ice, between particles and fields. Nothing is truly static. Everything is in motion, everything is transforming, everything is connected to everything else in ways both subtle and profound. Here's a thought experiment that might seem like science fiction, but which some scientists take seriously. What if Earth once had rings? Not now, obviously. We look up and see no rings encircling our planet. But perhaps in the distant past, billions of years ago, or perhaps more recently in geological terms, Earth might have been adorned with a ring system like Saturn's. How could this happen? One scenario involves the Moon. About 4.5 billion years ago, a Mars-sized object collided with the young Earth in a catastrophic impact. The debris from this collision, a mix of material from Earth's mantle and from the impactor, was ejected into orbit around Earth. Most of this debris eventually coalesced to form the Moon. But perhaps, before the Moon formed, the debris existed as a ring, a disk of molten rock and vaporized material orbiting Earth, gradually cooling and clumping together. Another scenario involves smaller impacts. Throughout Earth's history, asteroids and comets have occasionally struck the planet. If one of these impacts occurred at just the right angle and velocity, it might eject material into orbit rather than simply creating a crater. That orbiting debris could form a temporary ring, lasting perhaps thousands or millions of years before falling back to Earth or coalescing into small moonlets. There's no definitive evidence that Earth ever had rings, no geological record that clearly shows the effects of ring shadows or ring material raining down. But the absence of evidence isn't evidence of absence, and the idea is tantalizing. Imagine looking up at the night sky and seeing a bright arc stretching from horizon to horizon, dividing the heavens in two. Imagine the cultures that might have developed under such a sky, the myths and stories they would tell, the way rings would shape their understanding of the universe. Of course, if Earth had rings today, they would cause problems, blocking sunlight, interfering with satellites, complicating space launches. But in the distant past, or in some alternate timeline, rings might have been a beautiful addition to our planet, a reminder that Earth, like Saturn, is shaped by forces both violent and creative, by impacts and collisions that destroy and create in equal measure. Saturn's brightness, as seen from Earth, varies over time. This variation isn't because Saturn itself is changing, the planet remains consistent, but because of the rings, specifically because of how the rings are tilted relative to our line of sight. Remember, Saturn's rotation axis is tilted about 26.7 degrees, and the rings orbit in Saturn's equatorial plane. As Saturn moves through its 29.5-year orbit around the Sun, our viewing angle changes. Sometimes we see the rings tilted toward us, displaying their full width and catching maximum sunlight. Other times we see them edge on, where they appear as a thin line or disappear entirely. When the rings are tilted toward us and brightly illuminated, they reflect a tremendous amount of sunlight, so much that they can more than double Saturn's overall brightness as seen from Earth. Saturn, which normally shines at about magnitude 0.5 or 1.0, similar to bright stars like Rigel or Aldebaran, can brighten to magnitude 0, or even 0.5 when the rings are optimally displayed. That's a significant difference, enough to make Saturn one of the brightest objects in the night sky, easily visible to the naked eye even from light-polluted cities. Conversely, when the rings are edge-on, their contribution to Saturn's brightness nearly disappears. The planet dims, sometimes by as much as a factor of 2, becoming less prominent in the sky. This cycle repeats every 15 years or so, a gradual brightening and dimming tied to Saturn's orbital position and the changing geometry between Earth, Saturn, and the Sun. Ancient astronomers didn't understand why Saturn's brightness varied. They couldn't see the rings with the naked eye, so the changes seemed mysterious, as if Saturn itself were pulsing, brightening and dimming for reasons unknown. Now we understand. The rings are the answer. Those vast, shimmering structures, composed of countless ice particles, act like cosmic mirrors, catching sunlight and throwing it across the solar system. And when the geometry is right, when the rings are tilted just so, they make Saturn shine. A beacon in the darkness, visible across 1 billion kilometers, beautiful and bright and impossible to ignore. Saturn is not alone. It's accompanied by a vast family of moons, at least 146 confirmed so far, with more being discovered regularly as our telescopes improve and our surveys become more thorough. This makes Saturn's system like a miniature solar system, with more satellites than any other planet, each one following its own orbit, each one with its own characteristics and history. These moons range dramatically in size. At the large end is Titan, bigger than the planet Mercury, with a thick atmosphere and methane lakes. At the small end are irregular chunks of rock and ice, sometimes only a few kilometers across, barely distinguishable from the asteroids and comets that populate the outer solar system. Some of Saturn's moons are spherical, shaped by their own gravity into round worlds. Others are irregular, lumpy, potato-shaped, too small for gravity to overcome the structural strength of rock and ice. Some of Saturn's moons orbit close to the planet, embedded within or just beyond the ring system. These inner moons interact gravitationally with the rings, shaping their structure, creating gaps and waves, shepherding ring material through their gravitational influence. Other moons orbit much farther out, taking months or even years to complete a single orbit. Some of these outer moons move in retrograde orbits, orbiting opposite to Saturn's rotation, which suggests they weren't formed alongside Saturn, but were captured later. Asteroids or cometary nuclei that wandered too close and were snared by Saturn's gravity. And there are likely more moons yet to be discovered. Many of the recently discovered moons are tiny, only a few kilometers across, and difficult to detect even with powerful telescopes. There could be dozens, perhaps hundreds, of small moonlets orbiting Saturn that we simply haven't noticed yet. Each discovery adds to the complexity of Saturn's system, revealing new interactions, new dynamics, new pieces of the puzzle. It's a reminder that planetary systems are not simple. They're not just a planet and a few moons orbiting in neat, predictable patterns. They're chaotic, diverse, filled with objects of all sizes and compositions, interacting in ways both subtle and dramatic. Saturn's family of moons is like an extended family, diverse in character, connected by gravity, each member playing a role in the larger story. Let's turn our attention now to Titan, because Titan deserves special consideration. This moon, Saturn's largest, is extraordinary in nearly every way. It's bigger than Mercury, with a diameter of about 5,150 kilometers, 3,200 miles. Only Jupiter's moon Ganymede is larger among all the moons in the solar system. But Titan's size isn't what makes it remarkable. What makes Titan truly special is its atmosphere. Titan is the only moon in the solar system with a substantial atmosphere. Not a thin wisp of gas barely clinging to the surface, but a thick, dense atmosphere, thicker than Mars's, thicker even than Earth's in terms of mass per unit area. If you were standing on Titan's surface, you'd experience atmospheric pressure about 1.5 times that of Earth at sea level. You wouldn't need a pressurized suit. You'd need oxygen to breathe, of course, and extreme cold protection. Titan's surface temperature is 179 degrees Celsius, 290 degrees, but the pressure itself wouldn't crush or suffocate you. Titan's atmosphere is mostly nitrogen, just like Earth's, about 95% nitrogen, with most of the rest being methane. This similarity is striking. Earth and Titan are the only two worlds in the solar system with nitrogen-dominated atmospheres. But the similarities end there. Titan's atmosphere is opaque, shrouded in a thick orange haze composed of complex organic molecules. From orbit, you can't see Titan's surface at all, just the uniform, featureless haze that blocks visible light. This haze is created by photochemistry in Titan's upper atmosphere. Sunlight breaks apart methane molecules, and the resulting fragments recombine into more complex molecules, ethane, propane, acetylene, and eventually into long-chain hydrocarbons and organic compounds called tholins. These tholins are responsible for the orange color. They're essentially smog, natural, unbreathable, but chemically fascinating. And they rain down onto Titan's surface, slowly accumulating over millions of years, building up layers of organic material that blanket the moon. Titan is, in many ways, a laboratory for studying the chemistry that might have existed on early Earth, before life emerged, before oxygen filled the atmosphere. It's a world where organic molecules are constantly being created and destroyed, where chemistry happens on a planetary scale, where the ingredients for life are abundant, even if life itself is absent. And maybe as you imagine Titan, that hazy orange world, larger than Mercury, wrapped in nitrogen and smog, orbiting slowly through Saturn's shadow, you can appreciate how diverse the solar system is. How many different kinds of worlds exist? How each one is shaped by different forces, different histories, different combinations of temperature and pressure and chemistry. Titan has weather, actual honest-to-goodness weather, with clouds and rain and seasonal changes. But the substances involved are different from Earth's weather. On Earth, water evaporates from oceans, rises into the atmosphere, condenses into clouds, and falls as rain. On Titan, the same process occurs, but with methane instead of water. Methane on Titan behaves the way water does on Earth. At Titan's surface, temperature of 179 degrees Celsius to 90 degrees Celsius, methane exists in all three phases: solid, ice, liquid, and gas. Liquid methane pools on the surface in lakes and seas. Methane vapor rises into the atmosphere, condenses into clouds, and falls as rain. The rain carves channels in the landscape, creating river valleys and drainage patterns that look remarkably similar to those on Earth. Scientists call this the methane cycle, and it's analogous to Earth's water cycle: evaporation, condensation, precipitation, runoff, and back to evaporation. But there are differences. Methane is less dense than water and has different surface tension properties, which means methane rain falls more gently than water rain. The droplets are larger, falling more slowly in Titan's thick atmosphere and lower gravity. A methane rainstorm on Titan might feel more like a gentle mist than a downpour, each drop drifting lazily toward the ground. Titan's clouds are also made of methane, forming high in the atmosphere where temperatures are cold enough for methane to condense. These clouds are patchy, not covering the entire moon uniformly, and they appear and disappear with Titan's seasons. Yes, Titan has seasons. Saturn's tilt creates seasonal variations in sunlight, and these variations affect Titan's weather. During Titan's northern summer, clouds tend to form more frequently in the northern hemisphere. During southern summer, the pattern reverses. There's something almost familiar about Titan's weather, despite the alien substances involved. Clouds form, rain falls, liquids flow across the surface and collect in pools. It's a cycle we understand intuitively because we see it on Earth every day. And yet, it's happening with methane at 179 degrees C on a moon orbiting Saturn, a billion kilometers from Earth. It's a reminder that the same physical principles, thermodynamics, fluid dynamics, phase changes, apply everywhere. That weather, in some form, can exist on any world with the right combination of temperature, pressure, and volatile substances. And that home, in a sense, is not a single place but a pattern that can emerge in different forms, on different worlds, using different ingredients, but still recognizable as something we understand. Titan's surface is dotted with lakes, hundreds of them, concentrated primarily in the polar regions, ranging in size from small ponds to vast seas. The largest, Kraken Mare, is bigger than the Caspian Sea on Earth, with a surface area of about 400,000 square kilometers, 154,000 square miles. These aren't lakes of water, of course. They're filled with liquid methane and ethane, hydrocarbons that remain liquid at Titan's frigid temperatures. When the Cassini spacecraft used its radar to map Titan's surface, the lakes appeared dark. Radar waves don't reflect well off smooth liquid surfaces, but occasional bright spots suggested waves. Yes, waves. Ripples crossing the surfaces of Titan's lakes, driven by wind in the thick atmosphere. These waves are tiny compared to ocean waves on Earth, only a few centimeters high at most, because methane is less dense than water, and the wind on Titan is relatively gentle. But they're there, undeniable evidence that Titan's lakes are dynamic, not frozen or static. The shorelines of these lakes are surprisingly Earth-like. Radar images show bays and inlets, peninsulas and islands, drainage channels where rivers flow into the lakes. Some lakes appear to have beaches, gentle slopes, where the liquid meets the solid ground. And the liquid levels change over time, rising and falling with Titan's seasons as methane evaporates or precipitates, as rain falls or droughts persist. But swimming in these lakes would be impossible, even if you could survive the cold. Methane and ethane are much less dense than water, about 0.4 to 0.5 grams per cubic centimeter compared to water's 1.0. You wouldn't sink in a Titan lake. You'd float impossibly high, with most of your body above the surface. And if you tried to swim, the liquid would feel strange. More like rubbing alcohol than water, with very low surface tension and viscosity. Still, there's something profoundly moving about the fact that Titan has lakes, that there's another world in our solar system where liquid pools on the surface, where rain falls and fills basins, where shorelines shift and waves lap gently against alien beaches. It's not water, it's not Earth, but it's liquid nonetheless, a different kind of ocean under a different kind of sky, reflecting a different kind of light, but still recognizable as a lake, still obeying the same physical laws, still existing in that strange and wonderful state between solid and gas that we call liquid. Now let's shift our focus to another of Saturn's moons, much smaller than Titan, but no less fascinating, Enceladus. This little world is only about 500 kilometers, 310 miles, in diameter, small enough that you could drive around its equator in a day if there were roads. But Enceladus is far from inactive. Its south polar region is one of the most geologically active places in the entire solar system. From Enceladus's south pole, enormous plumes of water vapor and ice particles erupt into space, shooting hundreds of kilometers above the moon's surface. These aren't volcanic eruptions in the traditional sense. There's no molten rock involved. Instead, they're geysers, powered by the warmth of a subsurface ocean that lies beneath Enceladus's icy crust. Cassini flew through these plumes multiple times, sampling their composition. The results were astonishing. The plumes contain not just water, but also salts, organic molecules, silica particles, and even molecular hydrogen. The salts suggest that the subsurface ocean is in contact with a rocky seafloor, dissolving minerals from the rock. The silica particles suggest hydrothermal activity, hot water interacting with rock at the ocean bottom, similar to the hydrothermal vents found in Earth's deep oceans. And the molecular hydrogen suggests ongoing chemical reactions between water and rock, reactions that could provide energy for life. In other words, Enceladus has all the ingredients for life as we know it: liquid water, organic molecules, and a source of chemical energy. It's one of the most promising places in the solar system to search for extraterrestrial life. And the fact that its ocean is venting into space, shooting its contents up through cracks in the ice, means we don't even need to land on Enceladus or drill through kilometers of ice to study it. We can simply fly through the plumes and collect samples, something Cassini did, and something future missions might do again with more sophisticated instruments. Enceladus is a reminder that life might not be where we expect it, not on the surface of planets warmed by their sun, but deep beneath the icy crusts of small moons, warmed by tidal heating, sustained by chemistry rather than sunlight. It's a reminder that the universe is full of possibilities, full of environments we're only beginning to understand, full of places where the improbable might be real. Let's linger a bit longer with Enceladus, because what Cassini discovered in those plumes deserves more attention. When the spacecraft flew through the jets of water vapor and ice erupting from Enceladus's south pole, its instruments detected something remarkable: complexity. Not just simple water molecules, but a rich mixture of compounds that told a story about what's happening deep beneath the ice. The organic molecules detected include simple compounds like methane, ethane, and propane, but also more complex substances, some containing carbon-nitrogen bonds, some containing multiple carbon atoms linked together. These are the building blocks of life, the raw materials from which biological molecules are constructed. Their presence doesn't mean life exists on Enceladus, but it means the chemistry necessary for life is happening there. Organic synthesis, the creation of complex molecules from simpler ingredients. The salts, primarily sodium chloride, ordinary table salt, along with carbonates and other minerals, tell us that Enceladus's ocean is salty, similar to Earth's oceans. This salinity comes from the ocean interacting with rock at the seafloor, dissolving minerals over millions of years. The concentration of salt can tell us how long the ocean has been in contact with rock, how much exchange has occurred, how mature the chemical system is. And then there are the silica particles, tiny grains of silicon dioxide, the same material that makes up sand on Earth. On Earth, silica forms when hot water flows through rock, dissolving silica, and then depositing it as the water cools. The presence of silica particles in Enceladus's plumes suggests that similar processes are occurring on the ocean floor. Hydrothermal vents, perhaps, where water heated to 90 degrees C, 194 degrees, or hotter rises through cracks in the rock, dissolving minerals and creating chemical gradients. On Earth, hydrothermal vents are oases of life in the deep ocean. Entire ecosystems thrive around them, powered not by sunlight, but by chemical energy, bacteria that metabolize hydrogen sulfide or methane. Creatures that feed on those bacteria, complex food webs built on chemistry rather than photosynthesis. Could similar ecosystems exist on Enceladus? We don't know. But the ingredients are there, the environment is there. And that's enough to make Enceladus one of the most tantalizing targets for astrobiology, for the search for life beyond Earth. Enceladus doesn't just shoot water into space for its own sake. Those plumes have consequences. They create structure. They shape the space around Saturn in ways that are visible even from Earth. Specifically, they create the E-ring, Saturn's outermost and largest ring, that vast, diffuse halo of ice particles we mentioned earlier. Here's how it works. When Enceladus's geysers erupt, they eject material at high velocity, fast enough to escape Enceladus's weak gravity. Some of this material falls back down, coating Enceladus's surface with fresh ice, but much of it escapes into orbit around Saturn. These escaped particles become part of the E-ring, adding to its mass, replenishing material that's lost through other processes. The E-ring, in turn, is constantly being eroded. Particles fall back onto Enceladus or other nearby moons. Some spiral inward toward Saturn. Others are lost to space, blown away by solar radiation pressure or ejected by gravitational interactions. But as long as Enceladus continues to erupt, as long as its subsurface ocean remains warm enough to drive those geysers, the E-ring will persist. It's a dynamic system, maintained not by permanence, but by constant renewal. In a very real sense, Enceladus is painting a ring around Saturn with its own ocean. Every molecule of water that erupts from those south polar geysers, every ice particle that escapes into space, contributes to a structure hundreds of thousands of kilometers across. It's as if Enceladus is exhaling, breathing out its interior, dispersing itself across the Saturn system in a slow, continuous exhalation that's been ongoing for millions of years. And maybe there's something beautiful in that, in the idea that a small moon, barely 500 kilometers wide, can create something so vast, that the internal warmth of a tiny world, heated by tidal flexing from Saturn's gravity, can manifest as a ghostly ring visible from across the solar system. That small causes can have large effects, that even the smallest objects can leave marks that extend far beyond themselves. Enceladus is small, but its influence is enormous. Its signature is written in ice across hundreds of thousands of kilometers of space. Among Saturn's many moons, few are as visually striking as Iapetus. This moon, about 1,470 kilometers, 9-10 miles in diameter, has a bizarre appearance. One hemisphere is bright white, reflecting most of the sunlight that hits it, while the other hemisphere is dark brown or black, absorbing light like charcoal. The contrast is extreme. The bright side has an albedo of about 0.5 to 0.6, while the dark side is closer to 0.03 to 0.05. It's as if someone painted half of Iapetus black and left the other half white, creating a cosmic yin-yang symbol. When Giovanni Cassini first observed Iapetus in 1671, he noticed something odd. He could see the moon when it was on one side of Saturn, but it seemed to disappear when it moved to the other side. He didn't understand why. Later observations with better telescopes revealed the answer. Iapetus is tidally locked to Saturn, always keeping the same face toward the planet. The leading hemisphere, the side that faces forward as Iapetus orbits, is dark. The trailing hemisphere, the side that faces backward, is bright. When Iapetus was positioned so that Cassini could see its trailing hemisphere, it was bright and visible. When it rotated to show its leading hemisphere, it became too dark to see with his telescope. But what causes this two-toned appearance? The leading theory involves thermal segregation. Iapetus orbits far from Saturn, about 3.5 million kilometers out, in a region where it's bombarded by material from the outer solar system. Some of this material comes from Phoebe, another of Saturn's moons, which orbits even farther out in a retrograde orbit and sheds dust as it goes. This dark material accumulates on Iapetus's leading hemisphere, darkening it. But that's only the beginning. Once the leading hemisphere becomes darker, it absorbs more sunlight and heats up. This warming causes ice on the surface to sublimate, to turn directly from solid to gas, and the water vapor migrates to the colder, brighter trailing hemisphere, where it refreezes. Over millions of years, this process concentrates ice on the trailing hemisphere and leaves behind darker, non-ice material on the leading hemisphere. It's a runaway process. The darker the leading side gets, the more it heats up, the more ice it loses, the darker it becomes. The result is the stark contrast we see today. Iapetus is a reminder that moons, like planets, can be sculpted by processes that take millions of years to unfold. That surfaces aren't static, but evolve, shaped by sunlight and gravity and the slow migration of materials. And that sometimes the universe creates beauty through contrast, through the interplay of light and dark, warmth and cold, accumulation and loss. But Iapetus's two-toned appearance isn't its only strange feature. Running along most of its equator is an enormous ridge, a mountain range essentially, that stretches for about 2,300 kilometers, 800 miles, and rises up to 20 kilometers, 12 miles, above the surrounding terrain. To put that in perspective, Mount Everest on Earth is about 8.8 kilometers high. This ridge is more than twice as tall, and it runs in a nearly perfect line along Iapetus's equator, giving the moon the appearance of a walnut. Where did this ridge come from? That's one of the great mysteries of Saturn's moon system. Several theories have been proposed, but none is entirely satisfying. One idea is that the ridge is the remnant of ancient tectonic activity. Perhaps Iapetus was once geologically active, and internal forces pushed up this massive structure along a line of weakness at the equator. But Iapetus is small and cold, and it's hard to imagine what could have powered such dramatic tectonics. Another theory suggests that the ridge is the remnant of a ring system that Iapetus once had. Perhaps early in Iapetus's history, it captured material that formed a ring around it. Over time, this ring material spiraled inward and crashed onto Iapetus's surface, piling up along the equator to form the ridge. It's a fascinating idea, a moon with its own rings, but there's no direct evidence that such rings ever existed. A third possibility is that the ridge formed when Iapetus was spinning much faster than it does today. If Iapetus once rotated every few hours, rather than the 79 days it takes now, centrifugal force would have caused the moon to bulge dramatically at its equator. As Iapetus slowed down due to tidal interactions with Saturn, the bulge might have partially solidified, leaving behind the ridge we see today. we don't know which explanation is correct. Perhaps none of them are. Perhaps the truth involves a combination of factors, or something we haven't thought of yet. But the ridge stands as a testament to Iapetus's complex history, to forces we don't fully understand, to events that occurred billions of years ago and left their mark in stone and ice. And maybe as you drift towards sleep, you can imagine that ridge, towering 20 kilometers above the surface, stretching 300 kilometers around the equator, casting long shadows across the two-toned landscape, silent and ancient and inexplicable. Mimas is a small moon, only about 400 kilometers, 250 miles in diameter, but it has a feature that makes it instantly recognizable: an enormous crater named Herschel. This crater is about 130 kilometers, 80 miles across, roughly one-third the diameter of Mimas itself. Its walls are 5 kilometers, 3 miles high, and its central peak rises 6 kilometers above the crater floor. The result is a moon that looks remarkably like the Death Star from Star Wars, a spherical object with a large circular feature dominating one hemisphere. The impact that created Herschel must have been catastrophic. When an object struck Mimas with enough force to excavate a crater this large, it came close to shattering the moon entirely. On the opposite side of Mimas from Herschel, the surface shows fractures and disrupted terrain. Shock waves from the impact traveled through the moon's interior, nearly tearing it apart from the inside. If the impactor had been slightly larger, or if it had struck at a slightly different angle, Mimas might have been destroyed. Saturn would have gained another ring, and we would never have known that Mimas once existed. But Mimas survived. Barely. It held together, its self-gravity just strong enough to prevent complete disintegration. And over the millions of years since the impact, Mimas has continued orbiting Saturn, carrying Herschel crater as a permanent scar, a reminder of the violence that shapes planetary systems. Mimas also plays an important role in shaping Saturn's rings. As we discussed earlier, Mimas's gravity creates the Cassini division through orbital resonances. Particles orbiting in that region are in a 1.2 resonance with Mimas. They complete exactly 2 orbits for every 1 orbit Mimas completes, and the repeated gravitational tugs gradually clear out the region. So Mimas, despite being small and heavily cratered, is an architect of Saturn's rings. It carves structure into the system through its gravitational influence, shaping the appearance of Saturn as seen from Earth. Perhaps there's a lesson in that even scarred, damaged objects can still play important roles. That survival, even survival of catastrophic events, doesn't mean becoming irrelevant or ineffective. Mimas could have been destroyed. Instead, it endured, and now it shapes the system around it in subtle but profound ways. Tethys is another of Saturn's mid-sized moons, about 1,060 kilometers, 660 miles in diameter. Its surface is heavily cratered, marked by billions of years of impacts, but one feature stands out: a massive canyon system called Ithaca Chasma. This canyon is enormous, about 100 kilometers, 60 miles wide, 3 to 5 kilometers, 2 to 3 miles deep, and stretching for about 2,000 kilometers, 1,040 miles, which is roughly 3/4 of Tethys's circumference. Ithaca Chasma is one of the largest canyon systems in the entire solar system, relative to the size of the body it's on. If you were standing on Tethys's surface, looking out across this canyon, it would stretch to the horizon and beyond, a vast scar carved into the icy surface. But how did it form? The leading theory is that Ithaca chasma formed when Tethys's interior froze. Tethys, like many of Saturn's moons, is composed mostly of water ice with a small rocky core. Early in its history, Tethys's interior might have been warmer, perhaps containing a liquid water ocean beneath the icy crust. But over time, as the moon cooled, this ocean gradually froze solid. When water freezes, it expands. Ice takes up about 9% more volume than the same mass of liquid water. So as Tethys's interior froze, the moon expanded slightly, like a water bottle left in the freezer that bulges or cracks. The icy crust couldn't accommodate this expansion without breaking, so it fractured, creating Ithaca chasma as a massive fault line where the two halves of the moon pulled apart. It's a reminder that ice, despite seeming solid and inert, is dynamic over geological timescales. It freezes, melts, expands, contracts, flows, cracks. And on a world like Tethys, where temperatures hover around 187 degrees, 305 degrees, ice behaves like rock, strong enough to maintain mountains and canyons, but brittle enough to fracture under stress. The landscape of ice worlds is shaped by forces we don't experience on Earth, except on the coldest winter days, when water pipes burst and pavement cracks, giving us a tiny glimpse of the processes that dominate the outer solar system. Most of Saturn's moons are tidally locked. They rotate at the same rate they orbit, always keeping the same face towards Saturn. This is the natural end state for moons orbiting close to a planet, where tidal forces gradually slow the moon's rotation until it synchronizes with its orbit. But Hyperion is different. Hyperion tumbles. Hyperion is irregularly shaped, roughly 360 by 280 by 225 kilometers, like a lumpy potato or a sponge. Its rotation is chaotic, unpredictable. Sometimes it rotates around one axis, sometimes around another. Its orientation changes constantly, and there's no pattern to it. If you were on Hyperion's surface, hypothetically, since landing would be nearly impossible, you'd never know which way down was. Saturn might be rising, setting, or overhead, and its position would change unpredictably with each passing hour. Why is Hyperion's rotation chaotic? The answer lies in its shape and its orbit. Hyperion's irregular shape means it doesn't have a single, stable rotation axis. Different parts of the moon respond differently to Saturn's gravitational pull, creating torques that push and pull Hyperion in different directions. Additionally, Hyperion is in orbital resonance with Titan. Hyperion completes exactly 4 orbits for every 3 orbits Titan completes. This resonance adds periodic gravitational nudges that further destabilize Hyperion's rotation. The result is chaos, not in the colloquial sense of disorder, but in the mathematical sense. Hyperion's rotation is deterministic. It follows physical laws, but it's also sensitive to initial conditions. A tiny change in Hyperion's orientation at one moment leads to dramatically different orientations later on. It's impossible to predict, even in principle, exactly how Hyperion will be oriented at a given time in the distant future. Hyperion also has a strange, sponge-like surface, pockmarked with deep craters that give it a honeycomb appearance. Scientists think this texture is created by the sublimation of ice. Water ice turning directly from solid to vapor when exposed to sunlight. The vapor escapes into space, leaving behind the rocky material that was mixed in with the ice, creating a low-density, porous surface. Hyperion is a reminder that not everything in the universe settles into predictable patterns, that some systems, Even simple mechanical systems like a moon rotating in space can exhibit chaos, behavior that's fundamentally unpredictable despite being governed by deterministic laws. And maybe there's something liberating in that. Maybe Hyperion, tumbling unpredictably through space, is a symbol of freedom, proof that even in a universe governed by gravity and physics, there's room for unpredictability, for systems that refuse to settle down, that remain perpetually surprising. Rhea is Saturn's second largest moon after Titan, with a diameter of about 1,530 kilometers, 950 miles. It's heavily cratered, ancient, composed mostly of water ice with a small rocky core. On the surface, Rhea seems unremarkable compared to moons like Titan or Enceladus. But observations from Cassini hinted at something extraordinary. Rhea might have its own ring system. The evidence came from Cassini's instruments detecting a dip in the number of energetic electrons near Rhea, a signature that could be explained by rings absorbing those particles. Additionally, there were hints of debris orbiting Rhea in a disk-like configuration. If true, this would make Rhea the only moon in the solar system known to have rings, a moon with rings orbiting a planet with rings, like nested Russian dolls. However, later observations failed to confirm the rings directly. No images showed them. No conclusive proof emerged. It's possible that Rhea once had rings, but they've since dissipated, or that the debris exists but is too faint or diffuse to detect easily. Or perhaps the initial observations were misinterpreted, and the electron signatures have another explanation. We don't know for certain, but the possibility remains tantalizing. If Rhea does have rings, or had them in the past, they would have formed differently than Saturn's rings. Perhaps from an impact that ejected material into orbit around Rhea. Perhaps from a small moon or captured asteroid that ventured too close and was torn apart by tidal forces. The mechanics would be similar to Saturn's rings, but on a much smaller scale, a miniature version, orbiting a world that itself orbits a ringed giant. And maybe there's something poetic about that. The idea of rings within rings, of structures repeating at different scales, of moons mimicking their planets. It's a reminder that the patterns we see at one level of complexity can reappear at another, that the universe has favorite structures it returns to again and again, modified slightly by local conditions, but fundamentally similar. Saturn's moons don't orbit independently. They're connected through gravitational interactions, their orbits linked by resonances, relationships where orbital periods are related by simple ratios. Mimas and Tethys, for example, are in a 1.2 resonance. For every orbit Mimas completes, Tethys completes exactly 2. Enceladus and Dione are in a 1.2 resonance as well. Titan and Hyperion are in a 4.3 resonance. These resonances aren't coincidences. They're the result of gravitational interactions over billions of years. When two moons happen to approach a resonance, when their orbital periods become close to a simple ratio, gravitational interactions between them can either push them away from the resonance or lock them into it, depending on the specific circumstances. Once locked, the resonances are stable. They persist, maintaining the mathematical relationship even as other orbital parameters slowly change. Resonances have profound effects. They can transfer energy and angular momentum between moons, causing some moons to slowly drift outward while others drift inward. They can excite orbital eccentricity, making orbits more elliptical. And this eccentricity, in turn, can generate tidal heating, the gravitational flexing that keeps moons like Enceladus warm inside, maintaining subsurface oceans and powering geysers. In a sense, Saturn's moons are like a musical chord, multiple notes playing simultaneously, their frequencies related by simple ratios, creating harmony rather than dissonance, the gravitational equivalent of a perfect fifth or a major third. And this harmony has been sustained for billions of years, maintained by the continuous gravitational dialogue between the moons, by the exchange of energy and momentum that keeps them locked in their intricate dance. Perhaps it's fitting that Saturn, the planet of rings, of structure, of visible order, also has a moon system characterized by resonances and mathematical relationships. It's as if the same organizing principles that create the rings also shape the orbits of the moons, creating a system where everything is connected, where nothing moves independently, where each object's motion influences and is influenced by every other object in an endless cycle of gravitational interaction. We've mentioned Prometheus and Pandora before as the shepherd moons that shape the F ring, but there's more to their story. These two moons don't just shepherd the ring, they also interact with each other in a fascinating way. Every few years, Prometheus and Pandora engage in a gravitational dance that causes them to swap orbital characteristics. Here's how it works. Prometheus orbits slightly inside the F ring, and Pandora orbits slightly outside it. But their orbits aren't perfectly circular, they're elliptical, and the ellipses are oriented differently. This means that once every few years, Prometheus and Pandora pass unusually close to each other. When this happens, their mutual gravitational attraction causes their orbits to change. Prometheus gains energy and moves to a slightly higher orbit. Pandora loses energy and drops to a slightly lower orbit. In effect, they trade places, not literally swapping positions, but exchanging orbital characteristics. This exchange is periodic, repeating roughly every 4 years. It's a delicate gravitational ballet, choreographed by the laws of orbital mechanics, playing out in the darkness of space with no audience except spacecraft and patient astronomers. And it has consequences for the F ring. Each encounter between Prometheus and Pandora perturbs the ring material, creating new kinks and braids, reshaping the structure we observe. Perhaps there's a metaphor here about relationships, about how two objects or people can interact in ways that change both of them, that transfer energy or momentum or influence from one to the other, that create patterns visible to outside observers even if the interaction itself is invisible. Prometheus and Pandora will continue their dance for millions of years, passing close, exchanging energy, moving apart, and then coming together again in an endless cycle. And the F ring, caught between them, will continue to braid and unbraid itself, responding to their influence, forever shaped by their gravitational dialogue. Let's turn our attention back to Saturn itself now, to the planet's atmosphere, that golden veil that obscures whatever lies beneath. Saturn's atmosphere is remarkably similar to the Sun's composition, and this isn't a coincidence. Both formed from the same primordial cloud of gas and dust that collapsed to create our solar system 4.5 billion years ago. The Sun captured most of that material, but the outer planets, Jupiter, Saturn, Uranus, and Neptune, managed to accumulate significant amounts before the solar wind swept the remaining gas away. Hydrogen dominates Saturn's atmosphere, making up about 96% of the total. This is the lightest, simplest element in the universe, just one proton and one electron. Helium comes next at about 3%, followed by trace amounts of methane, ammonia, water vapor, and other compounds. These trace gases, despite their small concentrations, are responsible for much of what we see in Saturn's atmosphere. Ammonia forms the crystals that give Saturn its golden color. Methane absorbs red light, contributing to the planet's overall hue. Water vapor, though rare, occasionally condenses into clouds in the deeper atmosphere. The composition changes with depth. Near the top of the atmosphere, where temperatures are coldest, only the most volatile substances remain as gases. Deeper down, as pressure and temperature increase, substances that would be solids or liquids on Earth's surface exist as dense gases or supercritical fluids, states of matter that don't quite fit into the categories of solid, liquid, or gas, but have properties of multiple states simultaneously. And deeper still, perhaps thousands of kilometers below the visible clouds, hydrogen itself transforms. The pressure becomes so intense, millions of times Earth's atmospheric pressure, that hydrogen molecules are forced so close together that they break apart. Electrons separate from their nuclei and move freely, like electrons in a metal. This is metallic hydrogen, a state of matter that doesn't exist naturally on Earth, but dominates the interiors of gas giants. It conducts electricity, generates magnetic fields, and behaves in ways we can only approximate in our most powerful laboratory experiments. Saturn's atmosphere is a reminder that familiar substances can behave in unfamiliar ways under extreme conditions. That hydrogen, the most abundant element in the universe, the simplest of all atoms, can transform into something strange and exotic when subjected to the crushing pressures inside a gas giant. And maybe, as you drift towards sleep, that's worth contemplating. How context changes everything. How the same substance can be radically different depending on its environment. How nothing has a single, fixed nature, but is always adapting, always transforming in response to the forces acting upon it. Now we come to one of Saturn's most mysterious and visually striking features, the hexagon. At Saturn's north pole, there's a jet stream, a fast-moving band of wind that forms a nearly perfect hexagonal shape. Each side of the hexagon is about 13,800 kilometers, 8,600 miles long, which means the entire structure is wider than Earth's diameter. The hexagon has been observed continuously since the Voyager missions in the early 1980s, which means it's persisted for at least 40 years, and likely far longer. Why a hexagon? Why not a circle, or an oval, or some irregular shape? Scientists have created laboratory experiments that produce similar hexagonal patterns in rotating fluids. But the exact mechanism on Saturn remains uncertain. The hexagon seems to be a standing wave, a stable pattern created by the interaction between different wind speeds at different latitudes. The jet stream forming the hexagon moves at about 320 kilometers per hour, 200 mph, while the surrounding atmosphere moves at different speeds, creating shear forces that might lock the jet stream into this geometric pattern. But the hexagon's stability is what's truly remarkable. Most atmospheric features, storms, jet streams, cloud patterns, are temporary, lasting days or weeks, or, at most, years. Earth's jet streams meander and shift continuously. Jupiter's great red spot, though long-lived, changes size and intensity over time. But Saturn's hexagon maintains its shape decade after decade, as if it's etched into the atmosphere rather than merely flowing through it. The hexagon's vertices, the corners where the straight sides meet, are particularly interesting. These corners remain sharp, well-defined, even though you'd expect turbulence to smudge them over time. Something about the dynamics of Saturn's atmosphere maintains these sharp corners, preserving the geometric precision that makes the hexagon so striking. Perhaps the hexagon is a glimpse into a deeper order beneath Saturn's chaotic atmosphere. Perhaps it's telling us something about how rotating fluids organize themselves under certain conditions that might exist elsewhere in the universe, on other gas giants orbiting other stars. Or perhaps it's simply a beautiful example of how mathematics emerges in nature, how simple physical laws can create complex structured patterns without any conscious design, without any blueprint, just through the interactions of fluid and rotation and gravity playing out over time. The hexagon isn't just a static pattern, it rotates. The entire structure spins around Saturn's north pole, completing one rotation every 10 hours and 39 minutes. This is close to Saturn's overall rotation period, but not quite the same. Different parts of Saturn rotate at slightly different rates because Saturn, being composed mostly of fluid rather than solid material, doesn't rotate as a rigid body the way a rocky planet would. This difference in rotation rates tells us that the hexagon is a deep atmospheric feature, not just a surface phenomenon. If it were confined to the uppermost layers of the atmosphere, it might rotate at a different rate entirely. But the fact that its rotation period is close to Saturn's overall rotation suggests that the hexagon extends deep into the planet, anchored to the underlying structure, connected to processes happening hundreds or even thousands of kilometers below the visible clouds. Inside the hexagon, at the very center, there's a massive hurricane-like vortex, a swirling storm with a well-defined eye, similar to hurricanes on Earth but far larger. The eye of this polar storm is about 2,000 kilometers, 1,240 miles across, roughly 50 times the size of a typical hurricane eye on Earth. Wind speeds around the vortex reach 540 kilometers per hour, 335 mph. Yet the eye itself remains calm, a region of descending air and clear skies surrounded by towering cloud walls. It's a storm within a hexagon, chaos contained within geometry, turbulence bounded by sharp edges, and it's been spinning there for decades, perhaps centuries or longer, powered by Saturn's internal heat and shaped by forces we don't fully understand. Perhaps it will spin there for centuries more, long after we're gone, a monument to the strange and beautiful ways that fluid and rotation and heat can organize themselves into patterns that defy our expectations. Let's focus for a moment on that eye, the calm center of Saturn's polar storm. On Earth, hurricane eyes are regions of descending air, where the storm's circulation creates a low-pressure zone at the surface. Air is drawn inward by the pressure gradient. But as it approaches the center, the Coriolis effect, the apparent deflection caused by Earth's rotation, prevents it from reaching the center directly. Instead, the air spirals inward, creating the eye wall, a ring of the most intense winds and precipitation. At the very center, air descends from above, warming and drying as it falls, creating the calm, often sunny conditions we associate with hurricane eyes. Saturn's polar vortex works similarly, but on a scale that dwarfs anything on Earth. The eye is 2,000 kilometers across, large enough that if you were somehow standing at its edge, You wouldn't be able to see the opposite wall even on the clearest day. The curvature of Saturn would hide it beyond the horizon. And the winds around the eye wall? They reach 540 kilometers per hour, faster than the fastest winds ever recorded on Earth, sustained continuously year after year, with no sign of weakening. On Earth, hurricanes are powered by warm ocean water. They form over tropical seas, draw energy from the temperature difference between the warm surface and the cold upper atmosphere, and dissipate once they move over land or cooler water. But Saturn has no ocean, no surface, no warm and cold regions in the way Earth does. Saturn's polar vortex is powered by something else, probably the planet's internal heat, rising from the depths, creating convection currents that organize into this massive storm. And unlike Earth's hurricanes, which last days or weeks, Saturn's polar vortex is apparently permanent. It's not a storm that formed recently and will eventually dissipate. It's a feature of Saturn's atmosphere, as persistent as the hexagon that surrounds it, perhaps as old as the planet itself. A storm that has raged for billions of years, never touching land, never running out of energy, spinning endlessly in the darkness near Saturn's pole. For years, scientists wondered whether Saturn's south pole had a hexagon like the North Pole. For much of the Voyager and early Cassini missions, the South Pole was in darkness. Saturn's 29.5-year orbit means each pole spends about 15 years in winter, tilted away from the sun. But when southern spring arrived and sunlight began illuminating the South Pole, Cassini's cameras revealed something different. No hexagon. Instead, the South Pole had a massive vortex, similar to the one inside the northern hexagon, but without the surrounding geometric structure. This vortex was enormous, a hurricane-like storm with winds reaching hundreds of kilometers per hour, a well-defined eye, and spiral cloud bands stretching outward from the center. It looked in many ways like a more typical polar storm, the kind you might expect to find on any rapidly rotating planet with a thick atmosphere. But there was no hexagon. Why does the North Pole have a hexagon while the South Pole doesn't? Scientists aren't sure. It might have to do with subtle differences in temperature or wind patterns between the two hemispheres. It might be related to Saturn's seasons. The North Pole has been in sunlight for years now, while the South Pole is entering winter. And perhaps the hexagon is a feature that only appears under certain seasonal conditions. Or perhaps the difference is more fundamental, related to asymmetries in Saturn's interior or magnetic field that we don't yet understand. Or maybe, and this is speculative, the South Pole once had a hexagon too, but it broke down or transformed into the vortex we see now. Maybe hexagons aren't permanent after all. Maybe they're features that come and go on timescales longer than we've been observing Saturn, and we just happen to be living at a time when the North Pole has one and the South Pole doesn't. It's a reminder that even within a single planet, conditions can vary dramatically. That the laws of physics are universal, but their outcomes depend on initial conditions, on subtle differences that can lead to radically different results. Saturn's two poles, seemingly similar, have evolved different structures, and maybe that's true everywhere. That similarity doesn't guarantee sameness, that small differences can amplify over time, that the universe is full of variation, even within systems we think we understand. Saturn has seasons, just like Earth. The reason is the same. Its rotation axis is tilted relative to its orbital plane. Earth's axis is tilted 23.5 degrees, which is why we have summer and winter, longer days and shorter nights depending on the time of year. Saturn's tilt is 26.7 degrees, slightly more than Earth's, which means Saturn experiences seasons too. But Saturn's seasons are very different from Earth's. Because Saturn's year is 29.5 Earth years long, each season lasts about 7 Earth years. 7 years of summer, 7 years of autumn, 7 years of winter, 7 years of spring. Imagine living through a season that lasts longer than most human careers, longer than childhood or adolescence, a season that spans a significant fraction of a human lifetime. During summer in Saturn's northern hemisphere, that pole is tilted toward the sun. Sunlight strikes the northern latitudes more directly, providing more energy. The hexagon, bathed in continuous sunlight for years, becomes visible in detail. Clouds form more frequently. Storm activity increases. Meanwhile, the southern hemisphere enters winter. The South Pole tilts away from the sun, spending years in darkness, cooling gradually as the season progresses. And then, slowly, the seasons shift. Saturn continues its orbit, and the geometry changes. The North Pole begins tilting away from the sun, entering autumn and then winter. The South Pole begins tilting toward the sun, emerging from darkness into spring and then summer. The transition is gradual, almost imperceptible on human timescales, but inexorable. And Saturn's atmosphere responds. Wind patterns shift, temperatures change, storm activity migrates from one hemisphere to the other. Saturn's seasons are a reminder that time moves differently on different worlds, that a season isn't a fixed duration, but depends on the planet's year, its distance from the sun, its axial tilt. And maybe, as you lie there feeling the seasons of your own life, periods of growth and dormancy, light and darkness, activity and rest, you can appreciate that these cycles exist everywhere, playing out on different timescales, but fundamentally similar in their rhythm, their inevitability, their patient turning from one state to another. Every once in a while, roughly once per Saturn year, which means roughly every 30 Earth years, Saturn produces a spectacular display, a great white spot. This is an enormous storm, a convective outburst that erupts from deep within Saturn's atmosphere, punching through multiple cloud layers and creating a bright white plume visible even from Earth through amateur telescopes. The most recent great white spot occurred in 2010, erupting at northern mid-latitudes during Saturn's northern spring. The storm grew rapidly, expanding over the course of weeks, eventually wrapping entirely around Saturn's equator to form a continuous band. At its peak, the disturbed region was larger than Earth, visible as a bright streak against Saturn's normally smooth, golden appearance. Previous great white spots occurred in 1990, 1960, 1933, 1903, and 1876, a roughly 30-year cycle that corresponds to Saturn's orbital period. The correlation isn't perfect, and scientists aren't entirely sure what triggers these storms, but the timing suggests they're related to seasonal changes. Perhaps the slow warming of Saturn's northern hemisphere during summer creates conditions favorable for deep convection. Warm, moist air rising from the depths, breaking through overlying layers, and erupting into space. On Earth, we have similar phenomena, storms triggered by seasonal heating, by temperature differences between surface and upper atmosphere. But Saturn's great white spots are on a scale that dwarfs anything on Earth. They're planetary scale events, affecting vast swaths of the atmosphere, releasing energy equivalent to millions of lightning bolts, reshaping temperature and wind patterns for months or years after the initial eruption. And then, gradually, the storm subsides. The white plume dissipates, spreading out across latitudes, fading back into the golden haze. Saturn returns to its usual serene appearance, and we wait, watching, knowing that in another 30 years or so, the cycle will repeat. Another storm will erupt. Another great white spot will appear, reminding us that even the calmest, most placid-looking worlds harbor immense energies beneath their surfaces, waiting for the right conditions to unleash themselves in spectacular displays. The 2010 Great White Spot deserves a closer look because Cassini was there to observe it in unprecedented detail. The storm began as a small, bright spot at about 35 degrees north latitude. Amateur astronomers noticed it first, a new feature that hadn't been there the day before. Word spread quickly, and within hours, professional observatories were training their instruments on Saturn. Cassini, orbiting the planet, turned its cameras and spectrometers toward the growing disturbance. Over the next few weeks, the storm expanded explosively. It grew both in size and in intensity, churning out material that spread east and west along its latitude. The bright plume, a mixture of ammonia ice crystals and other compounds dredged up from deeper levels, wrapped around Saturn like a ribbon, extending farther and farther until it encircled the entire planet. The head of the storm, where the convection was most intense, met its own tail, creating a continuous band of disturbed atmosphere that stretched 300,000 kilometers, 186,000 miles, farther than the distance from Earth to the Moon. At its peak, the storm was generating lightning bolts at an astonishing rate. Cassini's radio instruments detected crackling bursts of radio waves, Saturn electrostatic discharges, or SEDs, produced by lightning in the storm clouds. These bursts were intense, indicating lightning strikes thousands of times more powerful than typical lightning on Earth. And they were frequent, occurring multiple times per minute during the storm's most active phase. The storm also disturbed Saturn's temperature patterns. Cassini's infrared instruments detected warming in the stratosphere above the storm, unusual beacons of enhanced temperature caused by waves propagating upward from the turbulent lower atmosphere. These temperature anomalies persisted for months after the storm's visible features had faded, indicating that the storm's effects extended far beyond the cloud layers we could see directly. Eventually, after several months, the storm began to subside. The convection weakened, the white plume gradually dispersed, and Saturn's atmosphere, though altered, began settling back toward its pre-storm state. But the memory lingered in the temperature anomalies, in the changed wind patterns, in the data Cassini collected, providing scientists with a wealth of information about how Saturn's atmosphere works, about what lies beneath those placid golden clouds, about the immense energies waiting to be released when conditions are right. Let's descend now, in our imaginations, through Saturn's atmosphere. We've been discussing the upper layers, the visible clouds, the storms, the hexagon, but what lies beneath? As we go deeper, the pressure increases. The weight of all the atmosphere above presses down, compressing the gas into denser and denser states. At first, the transition is subtle. The hydrogen remains gaseous, but becomes denser, hotter, more compressed. The temperature rises, not from sunlight, which can't penetrate this deep, but from the compression itself, and from Saturn's internal heat rising from below. Eventually, perhaps a few hundred kilometers down, the pressure becomes so great that hydrogen can no longer exist as a gas. It transitions to a liquid, not abruptly, but gradually, through a supercritical phase where the distinction between gas and liquid becomes meaningless. This liquid hydrogen ocean extends for thousands of kilometers. It's not like water. It's still extremely light, with a density far less than water's, but it flows like a liquid, convex like a liquid, carries heat from the interior toward the surface like a liquid, and the pressure continues to increase as we descend, the weight above becoming more and more immense. Eventually, at depths of perhaps 30,000 kilometers, about half of Saturn's radius, the pressure reaches a critical threshold, about 3 million times Earth's atmospheric pressure. At this point, hydrogen undergoes another transformation. The molecules, H2, two hydrogen atoms bonded together, are forced so close that they break apart. The electrons separate from the nuclei and become delocalized, moving freely through the material like electrons in a metal. This is metallic hydrogen. It conducts electricity. It generates magnetic fields through dynamo action. It has properties unlike anything we can create on Earth outside of the most extreme laboratory conditions, and it makes up a substantial portion of Saturn's interior, a vast ocean of liquid metal, thousands of kilometers thick, slowly churning and convecting, carrying heat and generating the magnetic field that surrounds the planet. We've never seen metallic hydrogen directly. We can't. It only exists under conditions we can't replicate or observe directly. But we infer its presence from Saturn's magnetic field, from theoretical models, from the behavior of hydrogen under extreme pressures in laboratory experiments. And maybe, as you drift towards sleep, you can appreciate the strangeness of it. That familiar hydrogen, the stuff that powers stars and makes up most of the universe, can become something so alien, so different from what we experience, simply by being compressed beyond our ordinary experience. 3 million atmospheres of pressure. Let's try to grasp what that means. Earth's atmospheric pressure at sea level is about 101,325 pascals, or roughly 14.7 pounds per square inch. It's the weight of all, the air above you, pressing down. You don't notice it because you're adapted to it, because your body is pressurized internally to balance the external pressure. Now multiply that by 3 million. At that pressure, matter behaves in ways that violate our intuitions. Substances that should be gases become solids. Solids become denser than we thought possible. Chemical bonds break and reform in unexpected ways. And hydrogen, simple, lightweight hydrogen, transforms into a metal. We have no direct experience with such pressures. The deepest we've drilled into Earth is about 12 kilometers, where pressures are only about 300 atmospheres. The deepest parts of Earth's oceans reach pressures of about 100 atmospheres. The center of Earth, where pressures are highest, reaches about 3.6 million atmospheres, comparable to the conditions where metallic hydrogen forms in Saturn. But we can't sample that material directly. We can only infer its properties from seismic waves and theoretical models. Saturn's interior exists in this extreme regime permanently, not as a brief moment in a laboratory experiment, but as a stable state maintained by the planet's immense mass. The metallic hydrogen layer is thousands of kilometers thick, containing more mass than many smaller planets, behaving according to physical laws we can barely test. And this metallic hydrogen is not static. It convects, hot material rises, cool material sinks, driven by the temperature difference between Saturn's core and its outer layers. This convection, combined with Saturn's rapid rotation, creates electric currents, and those currents generate Saturn's magnetic field through the dynamo effect. The same process that generates Earth's magnetic field, but on a vastly larger scale. Perhaps there's something humbling in knowing that most of Saturn's interior exists in a state we can barely study, governed by physics we can model, but not directly observe. That the universe contains conditions so extreme that our laboratories, our instruments, our direct experience are inadequate. That we must rely on inference, on mathematics, on indirect evidence to understand what's happening deep inside a world 1 billion kilometers away. Saturn's storms produce lightning, not the occasional flash we see in Earth's thunderstorms, but sustained, powerful electrical discharges that can persist for months. These lightning bolts occur deep within Saturn's water cloud layer, perhaps 100 to 200 kilometers below the visible ammonia clouds we see from orbit. The bolts themselves are hidden, but their radio emissions, called Saturn electrostatic discharges, or SEDs, can be detected by spacecraft and even by radio telescopes on Earth. Each lightning strike on Saturn is immensely powerful, perhaps 10,000 times stronger than typical lightning on Earth. The energy released in a single bolt could power a small city for days. And unlike Earth's lightning, which occurs in isolated storms scattered across the planet, Saturn's lightning often comes from storm systems that persist for weeks or months, generating hundreds or thousands of strikes during their lifetime. Cassini detected these radio bursts throughout its mission, tracking storm systems as they drifted with Saturn's winds, monitoring their intensity and duration. Some storms were quiet for weeks, then suddenly erupted in bursts of activity. Others maintained a steady drumbeat of lightning strikes, day after day, like a cosmic metronome marking time in the Saturnian clouds. The lightning tells us about conditions deep in the atmosphere, about the presence of water clouds, about vertical motion and convection, about energy being released from the depths and manifesting as visible storms above. Perhaps there's something mesmerizing about imagining those lightning bolts, crackling through clouds of ammonia and water, releasing energy in brilliant flashes that no human eye will ever see directly, yet detectable across millions of kilometers of space through the radio waves they produce. Saturn's storms are hidden beneath layers of haze, but their lightning announces their presence, a signal that says, here, beneath this calm surface, violence is occurring. Energy is being released. The atmosphere is alive. When a major storm erupts on Saturn, like the 2010 Great White Spot, it doesn't just create visible changes. It disrupts the entire atmospheric system in ways that cascade through multiple layers and persist long after the visible storm fades. The 2010 storm, for instance, altered Saturn's radio emissions for months. The planet's normal radio signature, a background hum of electromagnetic noise generated by charged particles in the magnetosphere, changed dramatically. New frequencies appeared. Intensities varied. The storm was essentially broadcasting its presence across the electromagnetic spectrum. Temperature patterns changed too. Infrared observations from Cassini revealed that the stratosphere, the layer above the storm, warmed significantly. Waves generated by the turbulent convection below propagated upward, carrying energy into regions that are normally stable and quiescent. These stratospheric beacons, bright spots in infrared images indicating elevated temperatures, appeared above the storm and persisted for months after the visible disturbance had subsided. The storm also affected wind patterns. The jet streams that normally flow smoothly at Saturn's latitudes were disrupted, their speeds changing, their structures becoming more turbulent. Material dredged up from deep layers, ammonia crystals, water vapor, trace gases, altered the chemistry of the upper atmosphere, changing how it absorbed and emitted light at various wavelengths. In a sense, a major storm on Saturn is like throwing a stone into a calm pond. The initial splash is dramatic, but the ripples spread outward, affecting regions far from the impact site, taking time to dissipate. Saturn's atmosphere, despite its immense size, is interconnected. Disturbances in one region propagate throughout the system, creating effects that can be measured halfway around the planet and thousands of kilometers above the initial event. Here's a puzzle. Saturn's upper atmosphere is hot, far hotter than it should be based on the amount of sunlight it receives. At the level where pressures are similar to Earth's atmosphere, temperatures are what you'd expect. Cold, around 178 degrees C. But higher up, in the thermosphere and exosphere, temperatures soar to 800 degrees C, 1470 degrees C, or higher. How is this possible? The sun's heating at Saturn's distance should keep the upper atmosphere cold, perhaps a few hundred degrees Kelvin at most, but observations show temperatures double or triple that. Something is pumping energy into Saturn's upper atmosphere, heating it far beyond what solar radiation alone can explain. One possibility is auroral heating. Saturn has auroras, just like Earth. Glowing curtains of light at the poles created when charged particles from the solar wind are funneled along magnetic field lines into the atmosphere. These particles carry energy, and when they collide with atmospheric molecules, they transfer that energy as heat. But Saturn's auroras are relatively weak compared to Jupiter's, and it's unclear whether they alone can account for the observed temperatures. Another possibility is wave heating. Waves generated deep in the atmosphere, perhaps by storms or by turbulence, propagate upward and break in the thin upper atmosphere, depositing their energy as heat. It's similar to how ocean waves break on a beach, releasing their energy in a burst of turbulent motion. Or perhaps there's interaction between Saturn's ionosphere and its magnetic field. Electric currents flowing through the tenuous plasma, generating heat through resistance. Scientists aren't certain which mechanism dominates, or whether it's some combination of all three. But the result is clear. Saturn's upper atmosphere is mysteriously warm, heated by processes we don't fully understand, defying simple explanations based on sunlight alone. When you look at Jupiter, you see structure, belts and zones of different colors, swirling storms, sharp boundaries between regions. Jupiter's atmosphere is visually complex, its dynamics on full display. But Saturn looks smooth, almost featureless. That golden yellow color is uniform across most latitudes, with only subtle variations visible even in detailed photographs. Why the difference? Both planets are gas giants with similar compositions. Both have banded wind patterns, jet streams, and atmospheric dynamics driven by internal heat and rotation. But Saturn has something Jupiter doesn't. a thick haze layer in its upper atmosphere. This haze is composed primarily of ammonia ice crystals, tiny particles that form when ammonia gas condenses in the cold upper atmosphere. These crystals are excellent at scattering light, diffusing it in all directions, which creates a uniform glow that obscures the structure beneath. Beneath this haze, Saturn's atmosphere is probably as complex and dynamic as Jupiter's. There are likely colored clouds at different depths: white ammonia clouds, brown and orange compounds created by photochemistry, perhaps even deeper water clouds, but we can't see them directly. The haze acts like frosted glass, softening everything, hiding the details, presenting only a serene, uniform surface to observers. This is why Saturn appears so calm and gentle compared to Jupiter's chaotic appearance. It's not that Saturn's atmosphere is less active. The 2010 Great White Spot proved otherwise. It's that Saturn hides its complexity behind a veil, revealing its turbulence only occasionally, when storms powerful enough to punch through the haze erupt from below. The rest of the time, Saturn maintains its dignified, peaceful appearance, like someone who keeps their struggles private, presenting a composed face to the world regardless of what's happening inside. We've discussed how Saturn radiates more energy than it receives from the Sun, about 2.5 times more. This excess heat has to come from somewhere, and one of the most intriguing explanations involves helium rain. Deep within Saturn, in the metallic hydrogen layer, conditions might be such that helium, normally mixed homogeneously with hydrogen, begins to separate out. Here's how it works. At the temperatures and pressures that exist deep in Saturn's interior, helium becomes less soluble in metallic hydrogen. It's similar to how oil and water separate. They can mix under certain conditions, but when conditions change, they phase separate, with one substance forming droplets within the other. On Saturn, helium condenses into liquid droplets that are denser than the surrounding metallic hydrogen. And being denser, they sink. These droplets fall, pulled by Saturn's gravity, descending through thousands of kilometers of metallic hydrogen on their journey toward the planet's core. And as they fall, they release energy, gravitational potential energy converted to heat through friction and compression. It's the same principle as hydroelectric power. Falling water releases energy. On Saturn, falling helium releases heat, warming the planet from within. This process has been ongoing for billions of years, slowly depleting Saturn's atmosphere of helium and concentrating it toward the core. Measurements of Saturn's atmospheric composition show that helium is indeed less abundant than expected compared to the Sun's composition, which supports the helium rain hypothesis. The helium isn't gone, it's just sunk, settling into the depths where we can't observe it directly. Perhaps in billions of years, most of Saturn's helium will have rained out, and the planet will cool significantly. But for now, helium rain keeps Saturn warm, keeps it glowing in infrared, keeps it radiating more energy than it receives. It's a reminder that planets aren't static. They're evolving, changing, slowly transforming over timescales that dwarf human history, but are mere moments in cosmic time. Let's shift now to talk about how we know what we know about Saturn. Much of our detailed understanding comes from a single spacecraft, Cassini. Launched in 1997, it arrived at Saturn in 2004 after a 7-year journey through the solar system, and then it stayed, orbiting Saturn, studying the planet and its moons, sending back data for 13 years until its mission ended in 2017. 13 years. That's longer than many human relationships last, longer than some careers, long enough to watch a child grow from infancy to adolescence. Cassini became a companion to Saturn, looping around the planet in a complex ballet of orbits designed to maximize scientific return. It completed 294 orbits total, each one carefully planned to fly by specific moons, to observe particular features, to position instruments for optimal measurements. Cassini carried 12 scientific instruments: cameras, spectrometers, magnetometers, radar, dust analyzers, each one designed to study different aspects of the Saturn system. It took over 450,000 images, capturing Saturn's rings in unprecedented detail, revealing storms and moons and structures that had never been seen before. It discovered 7 new moons, bringing Saturn's total to 146 and counting. It flew through Enceladus's plumes, sampled their composition, and revealed the existence of a subsurface ocean. It dropped the Huygens probe onto Titan, providing the first and only images from the surface of that distant moon. And then, in September 2017, with its fuel nearly exhausted, Cassini performed one final service. Rather than leave it in orbit, where it might eventually crash into one of Saturn's potentially habitable moons, mission controllers commanded it to dive into Saturn's atmosphere. Cassini plunged toward the planet, transmitting data until the very end, sampling Saturn's upper atmosphere directly before being crushed and vaporized by the increasing pressure. It was a fitting end, becoming part of the world it had studied for so long. Cassini's final plunge wasn't just poetic, it was necessary. The spacecraft, despite being carefully sterilized before launch, likely carried traces of Earth microbes. These hardy organisms, dormant but potentially viable, could survive in space for years or decades. And if Cassini, running out of fuel, had been left in orbit, it might eventually have crashed into one of Saturn's moons, perhaps Enceladus with its subsurface ocean, perhaps Titan with its organic chemistry and methane lakes. Such a crash would contaminate those worlds with Earth life, potentially compromising future searches for indigenous life. Even if the microbes couldn't survive or reproduce on these moons, their presence would create ambiguity. If we later detected signs of life, how could we be certain it wasn't contamination from Earth? The only way to eliminate this risk was to ensure Cassini never crashed into a moon. And the only way to guarantee that was to destroy it deliberately. So mission controllers designed the grand finale, a series of 22 orbits that took Cassini closer to Saturn than any spacecraft had ever ventured, threading the narrow gap between the planet and the innermost edge of the rings. These orbits provided unprecedented science. Measurements of Saturn's gravitational field, magnetic field, and ring mass, plus direct sampling of the ring particles and the planet's upper atmosphere. And then, on September 15, 2017, Cassini made its final plunge. As it entered the atmosphere, traveling at about 123 kilometers per hour, 76,000 mph, it began transmitting data, measuring atmospheric composition, temperature, pressure, until the signal was lost. Cassini had become a meteor, burning up in the skies of Saturn, its atoms mixing with the planet's atmosphere, ensuring it would never contaminate the pristine environments of Enceladus or Titan. It was planetary protection in action, science prioritizing the preservation of potentially habitable worlds over the convenience of leaving hardware in orbit. Cassini didn't travel to Saturn alone. It carried a passenger, the Huygens probe, built by the European Space Agency, designed for one purpose: to descend through Titan's atmosphere and, if possible, land on its surface. On Christmas Day 2004, Huygens separated from Cassini and began its coast toward Titan. 3 weeks later, on January 14, 2005, it entered Titan's atmosphere. The descent took 2.5 hours. Huygens fell through Titan's thick nitrogen atmosphere, protected by a heat shield from the friction of entry, then deploying a parachute to slow its fall. All the while, its instruments were active, taking images, measuring atmospheric composition, recording winds and temperatures. The cameras captured a world emerging from orange haze, river channels carved into ancient terrain, bright highlands and dark lowlands, features that looked eerily familiar despite being composed of ice and methane rather than rock and water. And then, remarkably, Huygens survived landing. It touched down on Titan's surface, a landing that hadn't been guaranteed since no one knew whether the surface was solid, liquid, or something in between. But the surface held. Huygens settled onto what appeared to be a damp, icy plain, perhaps a dried lake bed, surrounded by rounded pebbles of water ice. It transmitted data for about 90 minutes after landing, sending back images and measurements until its battery died, or until Cassini moved over the horizon and could no longer relay Huygens's signal. Those 90 minutes were precious. Huygens is the only spacecraft to have landed in the outer solar system, the most distant landing humanity has ever achieved. Its images and data revealed Titan as a world of stunning complexity, a place with weather, erosion, geological processes, perhaps even a subsurface ocean. And then the mission ended, as all missions must. Huygens fell silent, sitting on Titan's surface where it remains today, a monument to human curiosity, frozen and alone on the shore of a methane sea. Before Cassini, before Voyager, there was Pioneer 11. Launched in 1973, it was designed primarily to study Jupiter, but mission planners realized they could use Jupiter's gravity to slingshot Pioneer toward Saturn, making it the first spacecraft to visit the ringed planet. On September 1, 1979, Pioneer 11 flew past Saturn at a distance of about 21,000 kilometers, 13,000 miles, from the cloud tops. Close enough to feel the pull of Saturn's gravity. Close enough to take detailed measurements, but far enough to avoid the dangers of the ring plane. Pioneer 11's instruments were primitive by modern standards: simple cameras, basic magnetometers, particle detectors, but they revealed a wealth of new information. Pioneer discovered Saturn's F-ring, the narrow braided ring beyond the A-ring that we now know is shepherded by Prometheus and Pandora. It measured Saturn's magnetic field more accurately than ever before, revealing its unusual alignment with the planet's rotation axis. It detected charged particles trapped in Saturn's magnetosphere, analogous to Earth's Van Allen radiation belts, and it took images, grainy, low resolution by today's standards, but revolutionary at the time. Images of Saturn's rings edge on, revealing their thinness. Images of Titan's hazy atmosphere. Images of the planet itself, its banded structure faintly visible beneath the golden haze. These were the first close-up views of Saturn, the first time humanity saw the ringed giant as more than a fuzzy blur through telescopes. Pioneer 11 completed its flyby and continued outward, eventually leaving the solar system entirely. Its last communication with Earth was received in 1995, when it was about 6.5 billion kilometers from the Sun. Now it's in interstellar space, traveling silently through the darkness, carrying a plaque with images and information about Earth and humanity, just in case, someday, someone finds it. If Pioneer 11 was a reconnaissance mission, the Voyager missions were comprehensive surveys. Voyager 1 flew past Saturn in November 1980, followed by Voyager 2 in August 1981. Both spacecraft carried far more sophisticated instruments than Pioneer, including high-resolution cameras, spectrometers capable of analyzing atmospheric and ring composition, and instruments to study Saturn's magnetic field and charged particle environment. Voyager's images of the rings were spectacular. They revealed structure that ground-based telescopes had never seen. Thousands of individual ringlets within what appeared to be uniform bands, gaps and divisions carved by gravitational resonances, spiral density waves propagating through the ring material. They discovered the spokes in the B ring, those mysterious radial features that appear and disappear on timescales of hours. They imaged the F ring in detail, revealing its braided, kinked structure. The Voyagers also discovered new moons, 3 previously unknown satellites, tiny worlds orbiting within or near the rings, were spotted in Voyager images, and the spacecraft provided the first detailed looks at Saturn's known moons, revealing them as distinct worlds rather than mere points of light. Mimas with its enormous Herschel crater, Enceladus with its surprisingly smooth, young-looking surface, Iapetus with its stark, two-toned appearance. Perhaps most importantly, Voyager 2 flew close to Titan, using radio occultation, watching how radio signals passed through Titan's atmosphere to measure its density and composition. The data confirmed that Titan's atmosphere was thick and primarily nitrogen, and that methane was abundant. This set the stage for future missions, for Cassini and Huygens, for our current understanding of Titan as one of the most fascinating worlds in the solar system. Voyager opened the door. Later missions walked through it. On any clear night, if you know where to look, you can see Saturn without a telescope. It appears as a bright yellowish point of light, not quite as brilliant as Venus or Jupiter, but steady and unmistakable once you've learned to recognize it. Ancient observers noticed that Saturn, unlike the fixed stars around it, wandered slowly across the sky, moving through the constellations of the zodiac at its patient pace. This wandering behavior marked it as a planet, from the Greek word planets, meaning wanderer. But there's another way to distinguish Saturn from true stars. It doesn't twinkle. Stars twinkle because they're so far away that their light reaches us from what is essentially a single point. Earth's turbulent atmosphere bends and distorts that point of light, making it shimmer and dance. Planets, being much closer, appear as tiny disks rather than points, too small to see as disks with the naked eye, but large enough that atmospheric turbulence averages out across their parent size. The result is steadier light. Ancient astronomers noticed this difference without understanding the physics behind it. They could tell planets from stars not just by their motion, but by the quality of their light. Saturn shone with a calm, unwavering glow, fitting somehow for the planet named after the god of time and patience. Even today, finding Saturn with your naked eye connects you to thousands of years of human observation. You're seeing the same light that Babylonian astronomers recorded, that Galileo first glimpsed through his primitive telescope, that countless people throughout history have watched slowly moving through the stars. Saturn has been a companion to humanity for as long as we've looked up, a steady presence in the night sky, asking nothing, demanding nothing, simply existing in its orbit, visible to anyone who takes the time to look. Saturn's changing appearance through telescopes mystified early observers. For years, the rings would be visible, sometimes tilted one way, sometimes the other, but always present, always magnificent. And then, every 15 years or so, they would gradually fade and vanish, leaving Saturn looking like a simple sphere. Galileo witnessed this in 1612 and was baffled. He had seen Saturn with ears in 1610, but 2 years later, those ears had disappeared. He never solved the mystery before his death. The explanation is geometric. Saturn's rings lie in the planet's equatorial plane, and Saturn's axis is tilted 26.7 degrees relative to its orbit. As Saturn moves around the Sun, our viewing angle changes. For about 15 years, we see the rings from above or below, tilted toward us, their full glory on display. Then, as Saturn continues its orbit, the rings gradually appear more edge-on. Eventually, Earth crosses the ring plane, the moment when we're looking at the rings exactly edge-on. Because the rings are so thin, they become nearly invisible at this angle. Ring plane crossings happen roughly twice per Saturn orbit, once as we cross from viewing the rings from the north, and once as we cross back from the south. Each crossing lasts only a few weeks, but during that time, Saturn transforms. The magnificent ringed planet becomes a simple yellow sphere, its defining feature temporarily hidden by geometry. The next ring plane crossing will occur in 2025. If you have access to a telescope, it's worth watching Saturn during that period, witnessing the rings gradually shrink to a thin line and then disappear entirely. It's a reminder of perspective, of how what we see depends on where we stand, of how the most prominent features can vanish when viewed from a different angle. And then gradually, as Earth moves past the ring plane, the rings will reappear, tilting toward us once more, returning to their full glory. While Cassini provided incredible close-up views during its 13-year mission, the Hubble Space Telescope has been watching Saturn for even longer, since 1990 when it was first deployed. From its vantage point in Earth orbit, above the blurring effects of our atmosphere, Hubble can capture sharp images of Saturn year after year, creating a long-term record of how the planet changes. These observations have revealed Saturn's seasonal cycles in detail. Hubble images show how storms appear and disappear, how cloud patterns shift with the seasons, how the hexagon at the North Pole emerged from winter darkness as northern spring arrived. During Saturn's 2009 equinox, Hubble captured images of the rings edge-on, revealing vertical structures and subtle features that are normally overwhelmed by the ring's brightness. Hubble has also tracked the planet's atmospheric dynamics, how wind speeds vary with latitude, how storms evolve and dissipate, how Saturn's weather responds to seasonal heating. The 2010 Great White Spot, first spotted by amateur astronomers, was monitored in detail by Hubble, providing context for Cassini's up-close observations. Together, the two observatories, one in Earth orbit, one orbiting Saturn, created a comprehensive picture of the storm's development and impact. And Hubble continues watching. Even without a spacecraft at Saturn, even with Cassini gone, Hubble maintains its vigil, documenting changes, building a multi-decade record that reveals patterns impossible to see in shorter observation periods. It's a reminder that understanding requires patience, that some questions can only be answered by watching over years and decades, by building continuity across generations of scientists and instruments. For centuries, astronomers struggled with a fundamental limitation. Earth's atmosphere blurs celestial images. The same turbulence that makes stars twinkle also smears planetary details, limiting the resolution of even the largest telescopes. But in recent decades, a technology called adaptive optics has revolutionized ground-based astronomy, partially overcoming atmospheric blurring. Adaptive optics works by measuring atmospheric distortion in real time and correcting for it using deformable mirrors that change shape hundreds of times per second. These mirrors compensate for the atmosphere's wavefront distortions, essentially unblurring the light before it reaches the camera. The result is images nearly as sharp as those from space telescopes, sometimes even sharper, since ground-based telescopes can be much larger than space telescopes like Hubble. Modern observatories using adaptive optics can now capture Saturn in stunning detail. They can resolve individual cloud bands, track storms, monitor seasonal changes, even see some of the larger gaps in the rings. This democratizes Saturn observation. Institutions that can't afford space missions can still contribute meaningful scientific observations using ground-based facilities. It also means Saturn is more accessible than ever to professional astronomers worldwide. Teams in Chile, Hawaii, California, and other observatory sites can observe Saturn regularly, building comprehensive data sets that complement space-based observations. And when something interesting happens, a new storm, an atmospheric disturbance, multiple observatories can respond quickly, providing different viewing angles and wavelengths, creating a rich picture of dynamic phenomena. Perhaps there's something satisfying about this technological advancement. We haven't conquered the challenge of Earth's atmosphere. We've learned to work with it, to correct for it, to see through it. It's a reminder that obstacles aren't always absolute barriers. Sometimes, with enough ingenuity and persistence, we can find ways around them. Cassini's mission ended in 2017, and as of now, no follow-up mission is actively being built to return to Saturn. The gap between Cassini's end and the next Saturn orbiter will likely be decades. A frustrating reality given how much Cassini revealed, given how many questions remain unanswered. But missions are being proposed. Scientists have developed concepts for spacecraft that would return to Enceladus, perhaps flying repeatedly through its plumes with instruments specifically designed to search for biosignatures, organic molecules that might indicate life in the subsurface ocean. Other proposals target Titan, with concepts ranging from orbiters that would map the moon in detail to landers that would touch down on the surface, perhaps even submarines that could explore Titan's methane seas. These missions face practical challenges. Saturn is far away, requiring years of travel and significant fuel. Missions are expensive, billions of dollars, and compete with proposals for missions to other destinations. Mars, Europa, Venus, and various asteroids all have their advocates, their scientific cases for why they deserve the next major mission. Funding is limited, timelines are long, and tough choices must be made. But the scientific case for returning to Saturn is compelling. Enceladus might harbor life. Titan's organic chemistry might teach us about prebiotic processes that led to life on Earth. Saturn's rings might hold clues about planetary system formation. The planet's atmosphere, with its mysterious hexagon and powerful storms, remains poorly understood. There's more to learn, more to discover, more questions that can only be answered by going back. Perhaps in the 2030s or 2040s, a new spacecraft will launch towards Saturn, and perhaps a decade after that it will arrive, beginning a new chapter in our exploration of the ringed giant. Until then, we watch from afar, studying Saturn with telescopes, analyzing Cassini's data, planning for the day when we can return. Saturn's story begins with the birth of the solar system itself. About 4.6 billion years ago, a cloud of gas and dust, perhaps disturbed by a nearby supernova shockwave, began to collapse under its own gravity. Most of the material fell toward the center, forming the Sun. But some remained in a rotating disk around the young star, and from that disk, the planets formed. Saturn coalesced in the outer regions of this disk, where temperatures were cold enough for volatile compounds like water, methane, and ammonia to freeze into solid particles. These icy particles, along with rocky material, form the building blocks of Saturn's core, a seed of solid material, perhaps 10 to 20 Earth masses, that grew by accumulating material through collisions. Once this core reached a critical mass, its gravity became strong enough to capture gas directly from the surrounding nebula. Hydrogen and helium, the most abundant elements in the disk, flowed onto the growing planet, forming the massive atmosphere we see today. Saturn grew rapidly during this phase, accumulating most of its mass over a period of perhaps a few million years before the solar wind from the young sun swept away the remaining gas in the disk. The formation process left Saturn with its current composition, mostly hydrogen and helium, similar to the Sun, with a small rocky, icy core buried deep inside. And it left Saturn in its current orbit, about 9.5 AU from the Sun, in a region where it could remain stable for billions of years. Saturn has been there ever since, slowly cooling, slowly evolving, but fundamentally unchanged in its basic structure, a remnant of the early solar system, preserved across aeons. Saturn's formation location might not be where it is now. According to the Grand Tack hypothesis, the giant planets didn't form in their current orbits, but migrated significantly during the solar system's early history. Jupiter, in particular, might have spiraled inward toward the Sun, driven by interactions with the gas disk, before reversing course and migrating back outward. And Saturn? Saturn might have followed Jupiter inward, its own migration coupled to Jupiter's through gravitational resonances. The two planets moving together would have acted like cosmic shepherds, scattering smaller bodies, reshaping the asteroid belt, and potentially preventing the formation of a planet in the region we now know as the asteroid belt. But here's where it gets interesting. If Jupiter had continued its inward migration, it might have disrupted the inner solar system entirely, scattering or consuming the rocky planets that would become Mercury, Venus, Earth, and Mars. What stopped Jupiter was Saturn. When Saturn caught up to Jupiter and the two planets entered an orbital resonance, their gravitational interaction reversed Jupiter's migration, pulling both planets outward to roughly their current positions. If this hypothesis is correct, and it remains uncertain, then Saturn played a crucial role in making Earth possible. Without Saturn's presence, without the resonance that halted Jupiter's inward migration, the inner solar system might look very different. Earth might not exist, or might have ended up in a drastically different orbit, too hot or too cold for life to emerge. Saturn, in this scenario, is not just a beautiful planet, but a guardian, a world whose gravitational influence shaped the architecture of the entire solar system, creating the conditions that allowed our planet to exist. Saturn's orbit isn't static. Over immense timescales, it's slowly drifting outward, away from the Sun. The rate is tiny, about 0.1 AU per billion years, but the effect is real. In a billion years, Saturn will be noticeably farther from the Sun than it is today. In 10 billion years, it might be at 11 or 12 AU instead of its current 9.5 AU. What's driving this migration? The answer involves angular momentum exchange with smaller bodies in the outer solar system, objects in the Kuiper Belt, a region beyond Neptune filled with icy bodies left over from the solar system's formation. These objects occasionally pass near Saturn, and when they do, gravitational interactions transfer angular momentum. Saturn gains angular momentum and moves to a slightly higher orbit. The Kuiper Belt objects lose angular momentum and either fall inward or are ejected from the solar system entirely. This process is slow but relentless. Over billions of years, it gradually reshapes the outer solar system, moving the giant planets outward while scattering or removing smaller bodies. It's part of the ongoing dynamical evolution of the solar system, a process that began at formation and will continue until the Sun's eventual death. What will Saturn be like in the distant future, orbiting farther from the Sun? It will receive even less sunlight, making its already cold atmosphere colder still. Its internal heat will have diminished as the planet continues cooling. Perhaps its rings will be gone by then, their material long since rained down onto the planet or dispersed into space. Saturn will still be there, still orbiting, but changed, colder, darker, more isolated, a relic of an earlier, brighter age. We've mentioned this before, but it's worth emphasizing. Saturn's rings are temporary. The evidence comes from multiple sources, but one of the clearest is the rate of ring rain, the process by which charged ring particles spiral into Saturn's atmosphere. Cassini's measurements during its grand finale orbits quantified this rate, and the numbers are sobering. Saturn is currently losing ring material at roughly 10,000 kilograms per second. That's about 315 million kilograms per year, or about 315 billion kilograms per million years. The rings, even the massive B ring, don't contain infinite material. If you extrapolate backward, if you assume the rings have been losing mass at this rate since they formed, you arrive at an age of roughly 100 to 200 million years. Maybe a bit more if the erosion rate has varied, but certainly not billions of years. This contradicts the intuitive assumption that the rings formed along with Saturn. If they had, they should be 4.5 billion years old. But that's incompatible with the observed erosion rate. Something doesn't add up. Either the rings are young, formed relatively recently from a destroyed moon or captured comet, or there's some mechanism replenishing them that we don't understand. Most scientists favor the young rings hypothesis. It's simpler, requiring no unknown mechanisms. It suggests that what we see today is a temporary state, that Saturn has spent most of its existence without rings or with very different rings, and that we're living during a special time when Saturn happens to have this magnificent adornment. And if that's true, then every image of Saturn, every observation, every moment spent contemplating those rings becomes more precious. We're witnessing something fleeting, not on human timescales, but on planetary ones. 100 million years from now, the rings might be gone. And beings looking at Saturn then, if any exist, will see only a ringless sphere and wonder if we embellished our records. But what if the rings aren't a one-time occurrence? What if Saturn's ring system is cyclic, forming, evolving, dissolving, then forming again from new material? This is a speculative idea, not yet proven, but it's worth considering. The mechanism would involve Saturn's moons. Occasionally, perhaps every few 100 million years, gravitational interactions, collisions, or orbital perturbations might cause a moon to drift too close to Saturn, crossing the Roche limit and being torn apart by tidal forces. The resulting debris would form a new ring system, bright and massive at first, then gradually eroding over millions of years until it disappears. Meanwhile, other moons continue orbiting, and eventually another moon makes the fatal journey inward. Another ring system forms. The cycle repeats, creating periods with rings interspersed with periods without, over timescales much longer than human civilization, but brief compared to Saturn's age. If this hypothesis is correct, then Saturn has likely had multiple ring systems throughout its history, each one different from the last, each one lasting tens or hundreds of millions of years before fading away. And the rings we see today are just the latest iteration, the current chapter in a long story of ring formation and dissolution. This idea is comforting in a way. It suggests that Saturn's rings, while temporary on planetary timescales, aren't unique, that Saturn has worn rings before and will wear them again, that even though the current rings will eventually disappear, Saturn's nature as a ringed planet might persist across billions of years, maintained not by the permanence of any single ring system, but by the repeated creation of new ones. It's a kind of immortality through regeneration, not unlike how living organisms die, but life itself continues, renewed in each generation. Saturn was once just a beautiful curiosity, a planet with spectacular rings worth studying for its atmospheric dynamics and ring mechanics, but not particularly relevant to the search for life. That changed with Cassini's discoveries. Enceladus has a subsurface ocean containing organic molecules, salts, and an energy source that could support life. Titan has liquid lakes, complex organic chemistry, and conditions that might resemble early Earth before life emerged. These discoveries elevated Saturn's system to the top tier of astrobiological targets. If life exists on Enceladus, even simple microbial life, it would be the first confirmed example of life beyond Earth. And crucially, it would be an independent origin of life, not related to Earth life, not the result of panspermia or contamination. It would prove that life can arise independently under different conditions, that Earth isn't unique, that the universe might be teeming with life in places we never expected. Titan offers different questions. Not, does life exist there now? But could life arise there eventually? Or, does Titan's chemistry teach us about the prebiotic processes that led to life on Earth? Titan is a laboratory for studying organic chemistry on a planetary scale, a place where complex molecules form naturally, where liquids flow and cycle through an atmosphere, where conditions might mirror early Earth's reducing atmosphere. These possibilities, the chance of finding life or understanding how life begins, give Saturn's system profound importance beyond its beauty. It transforms scientific exploration into something more urgent, more compelling. The rings are still magnificent, the atmospheric dynamics still fascinating, but now there's an added dimension, the possibility that we might discover we're not alone, that life exists elsewhere in our solar system, orbiting Saturn, hidden beneath ice or dissolved in methane seas. Saturn has auroras, shimmering curtains of light that dance above its polar regions, visible in ultraviolet wavelengths, even though they're invisible to human eyes. These auroras work the same way Earth's do. Charged particles from the solar wind are funneled by Saturn's magnetic field toward the poles, where they collide with atmospheric molecules, exciting them and causing them to emit light. But Saturn's auroras are much larger than Earth's. The oval of auroral emission at each pole can be thousands of kilometers across, dwarfing the entire state of Alaska or the Scandinavian countries where Earth's northern lights are most visible. The energy involved is also much greater. Saturn's auroras emit as much power as millions of terrestrial lightning bolts, sustained continuously rather than flickering and fading like Earth's auroras. And there's another source of particles beyond the solar wind, Enceladus. The water vapor and ice particles erupting from Enceladus's geysers become ionized in space, and some of these ions are captured by Saturn's magnetic field. They spiral along field lines, eventually reaching the poles and contributing to the auroral display. In a sense, Enceladus is lighting up Saturn's poles, its water creating glowing curtains of light thousands of kilometers away. Cassini's instruments observed these auroras in detail, revealing how they respond to changes in the solar wind, how they brighten and dim with Saturn's rotation, how they're influenced by the planet's magnetic field and the supply of particles from Enceladus. It's a connected system: moon, magnetosphere, atmosphere, all interacting in ways that create beauty visible across the electromagnetic spectrum. We know surprisingly little about Saturn's deep interior. We can measure the planet's mass, its gravitational field, its rotation rate, but directly probing what's inside is much harder. On Earth, seismology, the study of how earthquake waves propagate through the planet, has revealed our internal structure in detail. We know the thickness of the crust, the composition of the mantle, the size of the core, all from analyzing seismic waves. But Saturn doesn't have earthquakes. It has no solid surface for waves to travel through. Its interior is fluid: liquid hydrogen, liquid helium, perhaps a small solid core, and sound waves propagate differently through fluids than through solids. And Saturn's rapid rotation complicates things further, creating equatorial bulges and flattening that affects gravitational measurements. Scientists have tried to infer Saturn's internal structure from its gravitational field, measuring how Saturn's gravity varies with latitude, which depends on how mass is distributed inside the planet. Cassini's grand finale orbits provided the most precise gravitational measurements ever, revealing subtle variations that constrain models of the interior. But constraints aren't the same as direct knowledge. We have models supported by data, but they're still models, mathematical constructions that fit the observations, but might not be unique. Perhaps future missions will find ways to probe Saturn's interior more directly, perhaps by studying oscillations, subtle vibrations of the planet that might propagate through the fluid interior. detectable as tiny variations in brightness or gravitational field. Or perhaps we'll simply have to accept uncertainty, acknowledging that some things are difficult to know directly, that we must rely on inference and modeling and the indirect evidence that physics provides. Here's a simple question with a surprisingly complicated answer. How long is a day on Saturn? You might expect this to be straightforward. Just measure how long it takes Saturn to rotate once. But Saturn is a fluid planet, and different parts rotate at different rates. The clouds at the equator rotate faster than clouds at higher latitudes. There's no solid surface to serve as a fixed reference point. On Earth, we can measure rotation by tracking landmarks, mountains, coastlines, cities. On Jupiter, we use the planet's magnetic field, which is generated deep in the interior and presumably rotates with the bulk of the planet. But Saturn's magnetic field is strange. It's aligned almost perfectly with the rotation axis, which makes it difficult to use as a reference. And worse, Saturn's magnetic field rotation period seems to change slightly over time, varying by several minutes over the course of Cassini's mission. Different methods give different answers. Radio emissions from the magnetosphere suggest one rotation period. Tracking clouds gives another. Oscillations in the gravitational field hint at yet another. Scientists have settled on a figure of about 10 hours and 33 minutes, but this comes with significant uncertainty, perhaps plus 30 minutes or more. Why does the magnetic field period change? No one knows for sure. Perhaps winds deep in the atmosphere are affecting the dynamo that generates the field. Perhaps there are oscillations or waves in the interior that modulate the rotation rate. Or perhaps we're simply measuring the wrong thing, using proxies that don't actually reflect the planet's bulk rotation. It's humbling to realize that even basic properties of a planet we've studied for decades remain uncertain, that how long is a day is a question we can't answer definitively for Saturn. Perhaps it's a reminder that some things are more complex than they appear, that simple questions can have complicated answers, that certainty is harder to achieve than we might hope. When Cassini flew through Enceladus's plumes, its mass spectrometer detected an array of organic molecules, not just simple compounds like methane and ethane, but more complex molecules, propane, acetylene, formaldehyde, and, most intriguingly, molecules containing nitrogen. These nitrogen-bearing organics are particularly interesting because nitrogen is essential for life as we know it, forming the backbone of amino acids, nucleotides, and other biological molecules. Some of the detected molecules are exactly the kinds of compounds you'd expect in prebiotic chemistry, the processes that might lead to life. They're not alive themselves, but they're the raw materials from which life could be constructed. Finding them in Enceladus's ocean suggests that the chemistry necessary for life is occurring there, that the ingredients are being mixed and reacted in ways that might, under the right conditions, lead to something more. Does this mean life exists on Enceladus? No, chemistry is not biology. Having the building blocks doesn't mean they've assembled into living systems, but it means the potential is there. The ocean has water, energy, and organic molecules, the three requirements generally considered necessary for life. Whether life has actually emerged is the central question motivating proposals for return missions. If life does exist on Enceladus, what would it look like? probably microbial, simple single-celled organisms, perhaps similar to the bacteria that live around hydrothermal vents on Earth's ocean floor. They might metabolize hydrogen or other chemicals, drawing energy from geochemistry rather than sunlight. They would be adapted to eternal darkness, to cold, to high pressure. But they would be alive, and that would change everything. Our understanding of life's prevalence in the universe, our sense of whether we're alone, our appreciation for the resilience and creativity of biology. Saturn's rings aren't just beautiful, they're scientifically valuable in unexpected ways. They provide a natural laboratory for studying how disks behave, how particles interact under gravity and collisions, how structures emerge from initially uniform distributions. And these processes aren't unique to Saturn's rings. They're relevant to other disk systems throughout the universe. Planet formation, for instance, begins with a disk of gas and dust around a young star. That disk gradually coalesces into planets through processes of collision, accretion, and gravitational interaction, processes we can observe directly in Saturn's rings. The propeller structures created by embedded moonlets in the rings are analogous to gaps carved by forming planets in protoplanetary disks. The spiral density waves in Saturn's rings mirror the spiral structures seen in disks around young stars. By studying Saturn's rings, we learn about these broader astrophysical processes in a system we can observe in detail. We can watch particles collide, see how they organize themselves, measure how gravitational resonances create structure. This informs our models of planet formation, helping us understand how Earth formed, how solar systems arise, how common planets might be around other stars. Accretion disks around black holes and neutron stars also follow similar physics. Matter spiraling inward, interacting through gravity and collisions, releasing energy through friction. Saturn's rings operate at vastly different scales and energies, but the underlying mathematics is often the same. Studying the rings teaches us about angular momentum transport, about how disks evolve over time, about the patterns that emerge when many particles interact under simple physical laws. In a sense, Saturn's rings are a gift, a system simple enough to observe and model, but complex enough to reveal principles that apply across the cosmos. A miniature universe spinning around a distant planet, teaching us about processes that shape galaxies and stars and planetary systems everywhere. We've mentioned this thought experiment before, but let's push it further and think about why it's impossible in practice. Saturn's density is 0.687 grams per cubic centimeter, less than water's 1.0 g/cm3. So theoretically, Saturn would float, but the size of the ocean required would be absurd. Saturn's volume is about 827 trillion cubic kilometers. An ocean containing Saturn would need to be vastly larger, and the gravity of that much water would be immense. Long before you could place Saturn in such an ocean, tidal forces would become significant. Saturn would be torn apart by the differential gravitational pull between its near side and far side, relative to the ocean's center of mass. Similarly, the ocean itself wouldn't remain stable. The gravitational forces involved would cause it to collapse into a sphere, or perhaps fragment into multiple bodies, or evaporate and dissipate into space. In reality, no such ocean exists or could exist. Water in quantities sufficient to float Saturn would have enough mass to form its own planet, or even star. The thought experiment is physically meaningless. It's like asking what would happen if you could travel faster than light, or divide by zero. The scenario violates so many assumptions built into physics that the question doesn't have a coherent answer. But the thought experiment remains valuable, not because it's practical, but because it highlights something genuine about Saturn: its remarkable lack of density. That a planet so vast, so massive compared to Earth, is composed of materials so light that it theoretically floats. It's a reminder that size and mass don't necessarily correlate, that volume and density are independent properties, that the universe contains objects that violate our intuitions about what a heavy and light mean. Saturn is still being born, not in the sense that it's actively forming. Its main accretion phase ended billions of years ago, but in the sense that it's still settling, still radiating the heat from that formation, still slowly contracting under its own gravity. The process is incredibly slow, but it's ongoing. Every second, Saturn releases more energy than it receives from the distant sun, and that energy has to come from somewhere. The source is gravitational contraction. As Saturn formed, gravitational energy was converted to heat, material falling inward, compressing, heating up through the work done by gravity. That heat is still there, trapped in Saturn's interior, slowly working its way toward the surface through convection and radiation. And as the heat escapes, Saturn cools and contracts slightly, which releases more gravitational energy, which sustains the heat flow. It's a slow feedback loop that will continue for billions of years. This process is different from how the sun generates energy. The sun is powered by nuclear fusion, hydrogen fusing into helium in its core, releasing energy that prevents further collapse. Saturn isn't massive enough for fusion. Its core temperature, though hot, isn't hot enough to ignite hydrogen. So Saturn has no internal energy source, except the gravitational energy from its formation, and the helium rain we discussed earlier. Eventually, in perhaps another 10 or 20 billion years, Saturn will reach equilibrium. It will cool to the point where it radiates only as much energy as it receives from the sun, assuming the sun still exists by then, which is uncertain. At that point, Saturn's contraction will effectively stop. The planet will have reached its final size, its final state, but that future is unimaginably distant. For now, Saturn continues its slow birth, continues radiating warmth into the void, continues the process that began 4.5 billion years ago and hasn't yet finished. Saturn's atmosphere is a time capsule. The hydrogen, helium, and trace compounds it contains were captured from the solar nebula when Saturn formed, and their isotopic ratios, the relative abundances of different versions of the same element, preserve information about conditions in that ancient cloud. For instance, deuterium, a heavy isotope of hydrogen with 1 proton and 1 neutron, as opposed to normal hydrogen's single proton, is present in Saturn's atmosphere in specific proportions. That ratio tells us about the temperature of the solar nebula and how efficiently deuterium was incorporated into Saturn during formation. Similarly, the ratio of helium-3 to helium-4, or the abundance of nitrogen-15 versus nitrogen-14, provides clues about nucleosynthesis in earlier generations of stars and about how material was processed in the solar nebula. These measurements are difficult, requiring sensitive spectrometers and careful analysis, but they're incredibly valuable. They link Saturn's current composition to the conditions that existed before the solar system formed, to the processes that created the elements we're made of, to the history of stellar evolution in our region of the galaxy. Saturn becomes not just a planet, but a witness, carrying evidence of events that occurred billions of years ago, preserving information that would otherwise be lost. And this information affects our understanding of planet formation more broadly. If Saturn's isotopic ratios differ from Jupiter's or from the Sun's, that tells us about how material was distributed in the solar nebula, about temperature gradients and mixing processes, about the timescales involved in planet formation. It constrains models, rules out scenarios, refines our understanding of how planetary systems arise from clouds of gas and dust. Saturn, in this sense, is an archive, a repository of data about the past, waiting for us to read and interpret its message. We've journeyed through 100 facts about Saturn, from the basic properties any textbook might list, through the strange details revealed by spacecraft, to the profound mysteries that remain unsolved. But perhaps the most important thing Saturn teaches us isn't a specific fact. It's a perspective, a way of seeing. Saturn reminds us that the universe is not hostile to beauty, that physical laws, gravity, electromagnetism, thermodynamics, can create structures of breathtaking elegance. Those rings, spinning around Saturn, aren't designed. They're the inevitable result of gravity and angular momentum, and collisions playing out over millions of years. The hexagon at the North Pole isn't planned. It emerges from fluid dynamics, from rotation, from simple forces interacting in complex ways. And yet these structures are beautiful. They inspire wonder. They make us pause and stare, whether we're looking through telescopes or at spacecraft images transmitted across 1 billion kilometers. That beauty isn't arbitrary or meaningless. It's telling us something about the universe itself. That order emerges from chaos. That complexity arises from simplicity. That the laws governing atoms and molecules and gravitational interactions can produce not just function, but art. Saturn is temporary. Its rings will disappear. Its storms will fade. Eventually, the sun will die, and Saturn will be cast into darkness, alone in the void. But for now, in this moment, Saturn exists as it is, a planet with rings, with moons, with mysteries and wonders that we're only beginning to understand. And in that existence, in those rings spinning silently through space, there's a kind of message that the universe is not just vast and indifferent, but also intricate and generous. That beauty exists not despite the laws of physics, but because of them. That wonder is not a human invention, but something we discover out there in the darkness, waiting patiently for us to notice. We've traveled together through Saturn's realm, from its golden clouds to its metallic hydrogen core, from the hexagonal storm at its pole to the geysers of Enceladus, from the braided F-ring to the methane lakes of Titan. 100 facts, 100 glimpses into a world so distant and strange, yet somehow familiar, a planet that reminds us of home even as it reveals how alien the universe can be. Saturn will still be there tomorrow, and the day after, and for billions of days beyond that. It doesn't need us to observe it, to study it, to wonder about it. But perhaps we need Saturn, need these moments of contemplation, these opportunities to step outside our daily concerns and consider something vast and patient and beautiful, something that existed long before us, and will endure long after we're gone, spinning quietly through the darkness, wearing its rings like a crown, asking nothing but offering everything to those willing to look. The rings are temporary. Our lives are temporary. Everything in the end is temporary. But temporary doesn't mean meaningless. Saturn's rings will disappear in 100 million years, but tonight, right now, they exist. They catch the light from a distant sun and scatter it across space, creating one of the most magnificent sights in the solar system. And you, wherever you are, have spent this time learning about them, contemplating them, allowing yourself to wonder. That's enough. That's everything. Rest now. Let Saturn continue its patient orbit. Let the rings spin in silence. Let the moons dance their gravitational ballet. Let Enceladus breathe water into space. Let Titan's methane rain fall on alien shores. Let the hexagon hold its shape at the pole. All of it will be there tomorrow, unchanged, waiting. And perhaps when you wake, you'll remember, if only for a moment, that somewhere far away, a planet named for the god of time is marking the passage of years with its slow orbit, reminding us that some things endure, that patience has its own beauty, that the universe is full of wonders we're only beginning to understand. Good night.